Now, time domain analysis. Time response analysis or time domain analysis that we are going to see. Time domain analysis. First, we must know that what is time response? Time response. Time response means the response of the system or output of the system. Both are same, one and the same. Response or output, both are same. Time response of the system is the output of the system as a function of time. If you plot the response, the output as a function of time versus magnitude, then it is called time response. We are plotting between time. At 0, the time we are giving input means, suppose the response is like this, then it is called time response. It is called time response. Time response means output of the system for a given input. For a given input. Output of the system for a given input with respect to time. Output of the system for a given input with respect to time. That is called time response. Here, various time responses are given. Various time responses are given. If you see the first response, this is the first response. Time is 12 seconds, 0 to 12 seconds. At the 0th time, the input is given, say step input. That's why it is called step response. Why it is called step response? The input is step input. What is step input? What is step input? Step input means you are giving step input to the lamp. You are giving step input to the fan. Initially, what is the value? Applied voltage to the fan, 0 volt. After that, what is the voltage? 230 volt. So you are giving a step input. You are giving a step input. This is time. This is time. At 0 time, t equal to 0, you are applying a voltage of 230 volt. It means you are giving a step input to the system. In this case, system is fan, or system is tube light, or system is some lamp. For that, you are giving a step input. So it means a constant input is given at t equal to 0. That is called step input. For that, if the system gives some output, means that output, the plot of the output between time and magnitude is called step response. That is called step response. So step response means the system's output for step input. The input may be magnitude. The input magnitude may be vary from one value to another. For example, in your fan, you are giving a step input of magnitude 230 volt. The magnitude is 230 volt. In this case, unit step input. Unit step input. Generally, we will give unit step input. Unit step input we will give. Unit step input means the magnitude is unity. The magnitude is unity. At t equal to 0, it will be raised from 0 to 1. This is step in, unit step input. At t equal to 0, the magnitude equal to magnitude, that is input x equal to 1, remains 1 up to infinity. Up to infinity remains 1. That is called step input. Step input. Unit step input. Such unit step input is given. Unit step input is given. Its response is plotted here. Its response is plotted here. Input is this. Input is not marked here. The red line is input. Unit step input. For that, the system is also going to that value 1. It follows the step input, but after some time, that is called sluggish response. Sluggish response. You already at t equal to 0, you gave input 1. You gave input 1. At t equal to 0, you gave input 1. But the system output is like this. It reaches 1 after some time. It reaches 1 after some time. That is natural. That is natural. It cannot follow with the input. Is it possible? Suppose I am giving input to a system. It has to respond for that input. Then only the output will come. After some time only it will come. That's why the response gradually increases and finally it reaches 1. So we can call this as sluggish response. Why? It takes a long time to reach the final value. It takes a long time to reach the final value for a step input. Another response is there. This is second response. This is first response. This is first response. That is sluggish response. You follow my pen. The second response. The second response is this. The second response is this. That is somewhat better while compare with 1. It is not sluggish. It is slow response. It is slow response. The second one is slow response. Second one is slow response. The third one is further quickly it reaches final value. It reaches quickly to the final value. Smartest response. Smartest response. Smartest response. Smartest means superlative degree. That's why it should follow input. That is ideal case. That is not possible. That is ideal case. If it that is the smartest. If it input and output are same, then that is smartest. But here that is the maximum possible. That is third case. That also reaches the final value as quickly as possible. We'll compare with 1, 2. It is faster. Quickly it reaches final value. All the 3, the difference is this is fast. This is fast. Third is very fast. 2 is slower. First is sluggish. Sluggish. Second one is slow. Third one is smartest. Another system is there. If you give input, it reaches beyond the final value. For example, 100-meter race. Are they stop at 100 meters? No, they are crossing 100 meters and running. It's not possible to stop at that point. Why? It's not possible to make the speed. Suppose they are running at some higher speed. They cannot make the speed at 0 immediately. That's not possible. Gradually they can reduce. That's why it reaches very fast. It comes vertically, no, very fast. It reaches the final destination, but it cannot stop there. That's why it goes beyond that value, then come down again the same velocity. Because of that, it oscillates, finally settles. Finally settles. You can notice whether you attended the electrical lab. Notice that indicating instruments, in that if you connect it, oscillates and finally settles. Poor damping systems will oscillate indicating instrument, not digital instrument. Nowadays, many are using digital instruments. But indicating instrument needle will go beyond that value, then come back again, it oscillates, finally it settles. That is the example. If you plot that response, it will be looking like that. Suppose I am connecting a 230 volt to that indicating instrument. How much I gave? Step input of 230 volt I gave. That meter goes beyond 230, then come down and oscillates. Finally, it settles at 230. So this is the response of that indicating instrument. Indicating instrument that oscillates for given input. That oscillates for given input. This is quick response. Response is quick, but it comes to final value quickly. No, it oscillates for some time, then finally it settles. Fourth response, quick and less oscillatory. Less oscillatory. But fifth response, if you see that, Fifth response, if you see that, it very quick and oscillatory. Very quick and oscillatory. Because speed is higher, that's why it quickly reaches the final value, but it cannot stop there. That's why it goes beyond that, then oscillates around that and finally settles. So there are 5 types of response. Sluggish response, slow response, smartest response, that is the maximum possible way. Then quick and less oscillatory. The fifth one is very quick and oscillatory. Very quick and oscillatory. There are 5 types of step response. Why it is called step response? The input is step input. For that, how the system behaves is step response. Both are step responses. What is the difference? The first one is sluggish. The second one is smart. Smart, but it oscillates. But it oscillatory. Why I am saying that it's smart? It reaches the final value quickly. At what time? Say at 1 second it reaches final value. Here, this is first time reaches the final value at 5th second only. Which is smart? The second one is smart. Because it reaches the final value quickly. In 1 second it reaches the final value. But it is oscillatory. That is different. It is oscillatory. That is different. But it has quickly it reaches the final value and oscillates around that value and finally settles. This transient part, this is called transient part. It is varying. It is not fixed. Varying, varying, varying. Finally, it reaches final and it remains there. That's why after this part is called steady state region. Steady state region. After this, before that it is varying. It is varying. Before that it is varying. That's why it is called transient. It is moving. That's why it is called transient response or transient region. Up to this, the response is called transient response. After that, it remains steady. In the indicating instrument in the lab, you might have seen, if you connect a 230 volt to the indicating instrument, it oscillates. Finally, it settles at 230 and remains at 230 only. Once it is settled at 230, then response is called steady state response. That is called steady state response. Before that, it is varying. That's why it is called transient response. So the response can be divided into 2 parts. One is called transient response. This part is called transient part. Transient response. This is steady state response. So response can be divided in 2 parts. This part is called, once it becomes steady, then it is called steady state response. Before that, it is varying. That's why it is called a transient response. Here also, up to this point, it is varying. Up to this point. Smart system, up to this point, it is varying. That's why up to this point, it is called transient response. Transient response. This part is called steady state response. After this, it is called steady state response. You understand this? Input. There are various types of inputs are there. The input may be a impulse input, step input. Already I explained what is step input. Step input means that t equal to 0, it will rise to a particular magnitude or remains in that value. That is called step input. Impulse input means that t equal to 0, you are giving input. Afterwards, its magnitude is 0. Before and after t equal to 0, its magnitude is 0. Can you give any example for impulse input? Mechanical example. Impulse input. Impulse input. Hammer blow. Hammer blow is an impulse input. Your hammer blow you are giving means a T equal to 0. The energy content in the hammer is transferred to that body. A T equal to 0. After that, no input. After that, no input. Hammer blow is an example. That is called impulse input. Impulse input. A T equal to 0, its magnitude is goes up to infinity. Ideal case, its magnitude goes up to infinity. But if you integrate that signal, from minus epsilon to plus epsilon, that signal is called del of t. That signal is called del of t. Started. Del of t. That signal, del of t dt. That signal is if we integrate this, its magnitude will be, if we integrate the signal, impulse signal, del of t is impulse signal. If we integrate this, its value will be unity. Unity, 1. Unity means 1. Or we can say A. Hammer blow, what is happening there? What is happening there? Energy in the hammer is transferred to that body. So, some energy is transferred from one body to another body. Energy is transferred from one body to another body. Here, the ideal case, its magnitude is infinity. Its width is 0. Its width is 0. Is it possible to have width of 0? Limiting case of 0. Limiting case of 0. Its magnitude is, its width is tends to 0. Width tends to 0. Similarly, height tends to infinity. Tends to infinity. Mathematically infinity. Width is mathematically 0. But is it possible to have a width of 0? Not possible. Ideal case. Width of 0, at t equal to 0, the energy is injected. If you draw the signal, I can draw this much duration. Hammer blow will be, sir, 10 millisecond. Hammer blow, how long it will be in touch with another body? The hammer blow, maybe 10 millisecond. 10 millisecond. Height is, say, height is A. Its width tends to 0. If width tends to 0, this magnitude will go to infinity. That is the meaning. If the width tends to 0, the magnitude goes to infinity because this is the fixed area. Fixed area. If it goes on decrease the width, what will happen? The height will goes on increase. If it goes to 0, definitely height will go to infinity. That is the meaning. That's why Bruce Lee becomes famous, because the point of duration of contact is very, very less. The duration of contact is very, very less. That's why his impact is very high. Impulse input. He is giving impulse input. That's why he became famous. The time of contact, the blow same, but time of contact is very less. That's why he became famous. So this is called impulse input. As width decreases, magnitude goes on increases. That's why this signal we cannot talk in terms of magnitude, impulse input. Energy content, we have to talk in terms of energy content. That's why integral of del of t from minus epsilon to plus epsilon. This is epsilon, minus epsilon to plus epsilon. This epsilon tends to 0. Epsilon tends to 0. It's the energy content equal to A. Then it is an impulse signal of magnitude A. Impulse signal of impulse input of magnitude A. Interchangingly, we will say input signal. Actually, here input energy. In control system, input is energy. That's why we can say input. Simply say input. Input signal also we can say it is not signal, actually energy. So the magnitude is A. The impulse function's magnitude is A. If you integrate, you will get A, because you are getting the area of this area you are finding. Integration means area. Suppose I am having a signal like this. If you integrate this signal, what you will get is, this is a signal. If you integrate this signal up to t, 0 to t, if you integrate that signal is x of t. X of t is varying like this. If you integrate this signal, what you will get? Up to t, you will get area under this curve. So similarly, that is energy content. Energy content. Here, you are finding the area by integrating this, but the epsilon tends to 0 because the signal is available only at t equal to 0, not at other points. It's not available. So its magnitude is A. Therefore, it is an impulse signal of magnitude A. Then unit impulse means A equal to 1. If A equal to 1 means it is unit impulse signal. Unit impulse signal. That's all. Step signal means its magnitude is A at t equal to 0 and remains A forever. Remains A forever. Then it is called step signal. If the magnitude is equal to unity means unit step signal or unit step input. In control system, we won't use the signal word. Unit input, unit step input, unit impulse input. Like that we will say. Okay. That is called step input. If we take Laplace transform of this, Laplace transform of del of t equal to 1. Laplace transform of unit impulse signal whose magnitude is A means Laplace transform will be A. Laplace transform of unit impulse signal means unit impulse input means its value is 1. Its value is 1. So Laplace transform of del of t equal to 1. If it is unit impulse input, Laplace transform of del of t equal to A if its magnitude is A. If its magnitude is A. That's all. Laplace transform of step input. Step input is normally represented by U of t. You might have studied in signals and system. U of t. U of t. If you find the Laplace transform of U of t, it's equal to 1 upon S. 1 upon S. If its magnitude is 1, if its magnitude is A means Laplace transform of U of t equal to A upon S. A upon S. So if you find the Laplace transform for that signal, it will give 1 by S, unit input. If it is magnitude A, step signal means A upon S. A upon S. You understand this point? So in frequency domain also we must know. Frequency domain also we must know. If you time domain, how U of t looks like in time domain? Time domain, it is looking like this. In frequency domain, it is 1 by S. In frequency domain, it is 1 by S. Already I told you that time and frequency are inversely proportional. That's why that infinity becomes 0 here in time domain. Time domain 0 becomes infinity in frequency domain. They are inversely proportional. Inversely proportional. You have to imagine like that. You have to imagine like that. So U of t, time domain, if you plot that unit step signal, it is looking like this. Time versus magnitude. If you take Laplace transform of unit step input, you will get 1 upon S. Impulse response, if you take Laplace transform, you will get 1. Unit impulse means impulse of magnitude A means you will get A. The third signal, ramp signal. The third signal is called a ramp. Ramp, it is like a ramp input or signal. In control system, we used to say input. Ramp input. It is like a ramp. It is go on increases up to infinity. Go on increases up to infinity. Time versus magnitude. Time versus magnitude. Ramp signal. Its slope, if its slope equal to 1 means unit ramp signal. slope equal to 1 means what? At 1 second, its magnitude will be 1. At 2 seconds, its magnitude will be 2. At 3 seconds, its magnitude will be 3. If it is increasing like that, at 45 degree, if it increases, then it is called unit ramp signal. Unit ramp signal. A ramp signal of magnitude A means its slope is A. Its slope equal to slope is A. At 1 second, its magnitude will be A. At 2 seconds, its magnitude will be 2A. At 3 seconds, its magnitude will be 3A. Like that, it will increase. That is called ramp signal of magnitude A. If we take Laplace transform of that ramp signal, A upon S square. If you take Laplace transform of ramp signal, A upon S square. Another signal is called parabolic signal. Parabolic signal. The third signal is called parabolic signal. It is increasing like exponentially. It is like not exponentially, parabolically it increases. That is called parabolic signal. That is proportional to that signal x of t is proportional to t square. Ramp signal, if you see that, it is proportional to x of t is ramp signal, proportional to t. As t increases, it linearly increases. It linearly increases. That's why it is straight line. Linearly increases means straight line, you know. Linear means the graph must be a straight line. That's why it is a straight line. U of x of t is proportional to t. If x of t is equal to t means unit ramp signal. Unit ramp signal. X of t equal to a means ramp signal of magnitude a. Ramp signal of magnitude a. If x of t equal to t, here coefficient is 1, 45 degree. As time increases, magnitude go on increases. Go on increases. At 1 second, its value is 1. At 2 seconds, 2. Then it is called x of t equal to t. So here, if you see the parabolic signal, x of t is proportional to t square. X of t equal to t square means unit parabolic signal. Unit parabolic signal. X of t equal to a t square means parabolic signal of a magnitude a. Normally, to have a convenient discussion among time domain and frequency domain, we will take a by 2. We'll take a by 2. If we take Laplace transform of this, you will get 2 by s square. You will get. If we take Laplace transform of a t square, you will get 2 by s square. 2 upon s square, you will get. To cancel that 2, normally we will take a by 2 t square. Magnitude will be taken a by 2 times. So in Laplace domain, x of s equal to a upon s square. We won't discuss a by 2, but that is the meaning. Magnitude of a is, while compare with ramp signal, it is half of the value of magnitude. That way we'll take a upon s square. A upon s square. Sorry, this is for ramp cube. Parabolic a upon 2 by s cube. If you take Laplace transform of this, 2a by s cube you will get. 2a by s square. If you take a by 2, 2 getting cancelled, that's why a upon s cube you will get. Convenient to discuss in both the domain. Because a is unknown, it can be taken any magnitude. A upon s cube for parabolic signal. So now we can Laplace domain, in time domain and Laplace domain, we'll write all signals. This is time domain. This is Laplace domain. This is x of t. Impulse first. Impulse signal. Impulse signal is what? Del of t. We'll write like then del of t. In Laplace domain, one step u of t equal to, if it is unit, all signals we will discuss only unity. U of t equal to t, equal to a, magnitude is 1. U of t equal to 1. Unit step input means u of t equal to 1. If you take Laplace domain, it becomes 1 by s. U of t equal to 1. Always the output is, the input is 1. Magnitude is 1 forever. From t equal to 0 to infinity, if it is 1, means u of t equal to 1. If you take Laplace transform, you'll get 1 by s. Ramp signal. Ramp signal means x of t equal to t. If we take Laplace transform, 1 upon s square. Parabolic input. Parabolic input. X of t equal to t square. T square. 1 by 2 t square. To cancel that 2. 1 by 2 t square in time domain. That's why in frequency domain, you will get 1 upon s cube you will get. 1 upon s cube you will get. That's all. If you know, these are the 4 standard signals will be applied to any system to discuss about characteristics. Suppose I want to test you, what I will do? Some input has to be given. Here the input is teaching. How you are responding in a test, that is the output. So I can find the behavior, characteristics of that system. We can study like that. There are many inputs are there to study about a system. The impulse input we can give and how it behaves in time domain. That is called the impulse response. We can study the characteristics of the system. We can give step input, we can study the characteristics of the system. We can give ramp input, we can study the characteristics. We can give parabolic input, we can study the characteristics. There are 4 standard types of input signals that we can give and study the characteristics of the system. You understand this? Most of the time we will apply only impulse and step. Rarely we will apply ramp and parabolic. Another signal we will apply, that is sinusoidal. Sinusoidal. Sine input. Sinusoidal input will apply to the system. If you want to do frequency response analysis, we will give sinusoidal input. That also we will see later. For frequency response, we used to give sinusoidal input. Varying input, but constant amplitude, but signal, constant maximum amplitude, but amplitude is varying like sinusoidal signal, sine signal. That also standard signal. So what are the standard signals? Impulse, step, ramp, parabolic, and sinusoidal. In frequency domain, we will study about sinusoidal signal. In time domain, most of the time we will study about impulse and step only. Transfer function. Transfer function. Already we studied. We found a transfer function for a given system in first unit, but not that. We do not know what is the meaning of that. Transfer function means we used to represent by G of S. Suppose I am having a system. This is the system G of S. I am representing the system by G of S. I am giving input. I am giving input R of T. R of T as input. The system responded for that R of T as C of T. C of T. Output is C of T. Input is R of T. It may be impulse input, or it may be a step input, or it may be a ramp input, or it may be a parabolic input, or it may be a sinusoidal R of T. Some signal. For that, what is the response? Output of the system is C of T. Input of the system is R of T in time domain. In frequency domain, what is the input of the system? R of S. What is the output of the system? C of S. I know the expression for C of S. I know the expression for R of S, means I can find the transfer function. C of S upon R of S is the transfer function of the system. That is mathematical model in transfer function representation. The Laplace transform of output upon Laplace transform of input is called transfer function. Laplace transform of output upon Laplace transform of input is called transfer function of the system. Transfer function of the system. So C of S upon R of S is called transfer function. The transfer function is represented by G of S. That's why in block diagram representation, you are putting G1, G2, G3. Sometimes some author used to say H of S also. G of S or H of S. They will represent the transfer function as H of S. We used to represent G of S. For feedback transfer function, we used to represent H of S. But the forward path transfer function also can be represented by H of S. It is up to the author, book's author, to represent G of S or H of S. Already I told you that why G1, G2, G3, many transfer functions are coming for a single system. Suppose the system is represented by 5 differential equations. You will get G1, G2, G3, G4, G5. For each transfer function, each equation, you will get one transfer function. For each equation, there will be one input, one output will be there for each equation. If you write a transfer function for that input output, you will get one transfer function, that is G1. For second equation, you will get one transfer function, that is G2. If you connect all these together, you will get the final system. You will get the final system, that is called block diagram representation. For that, we have seen 2 types of simplification to convert into one transfer function, G of S. I want to combine all G1, G2, G3, G4, G5 into single transfer function, G of S. There are 2 methods. One is block diagram reduction. Another one is signal flow graph representation. Once and for all, it is converted. You will get a transfer function like this. Finally, you will get like this. Finally, you will get like this. This is the transfer function, whose degree is n in the denominator, whose degree in the numerator is m. If the denominator is s, means n means it is actually represented by nth order differential equation. Nth order differential equation. Suppose the system is represented by second order differential equation, means n equal to 2. Therefore, that system is nth second order system. Second order system. Here, m, always numerator degree will be less than denominator degree. Always numerator degree will be less than denominator degree. Always n should be greater than m. Not greater than or equal to, we can say, but all practical system will be n will be greater. N will be greater. If m is greater, it's not physically realizable. Not physically realizable system. That's why if you get numerator degree higher, means it is not physically realizable. For example, I can find very good circuit. No one can find such circuit. But I can find mathematically. That circuit works very fine. It takes 0 energy. But a component required in that circuit is a resistance of -5 ohm. Mathematically, I got -5 ohm. Is it possible to get -5 ohm physically? Physically not possible. Physically not possible. So all physically realizable systems will have numerator degrees less than denominator degree. So always m is less than m. Always m is less than m. If it is greater, means it may not be a physically realizable system. Physically realizable. By looking at the transfer function, we can say that whether it is physically realizable or not. We can say, by looking at the transfer function, we can say that whether it is not only this, many aspects are there that we will see later. So if numerator degree is less than the denominator degree, then it is physically realizable. Another, in the previous class, we have seen introduction to time response analysis. Transfer function. Suppose I'm having a system . G of S. G of S is a system. The input to the system is R of T. Output of the system is C of T. The input to the system is R of T and the output of the system is C of T. If we take Laplace transform of C of T, you will get C of S. The same way, if we take Laplace transform of R of T, you will get R of S. The ratio between C of S and R of S is called transfer function. So, the model of the system is represented as ratio between the Laplace transform of output and input. Here you can notice that the degree of denominator degree of the transfer function is n. It means the system is nth order system. Suppose I'm having a second order system, means its mathematical model will have second order differential equation d square y by dt square plus b dy by dt plus c y equal to x. Suppose if you find a transfer function for this, that is output y of s upon x of s, if you find its degree will be 2. You can notice that a s square y of s plus b s y of s plus c y of s equal to x of s. Therefore, the output upon input y of s upon x of s equal to 1 upon a s square plus b s plus c. So, this degree indicates that the system is second order. So, this is starts with the s power n. The degree is n. Therefore, nth order system. Always the numerator degree is less than denominator degree. Or n is always greater than m. N is always greater than m. All physically realizable systems, the denominator degree will be higher than numerator degree. N always greater than m. Then only it is physically realizable. Otherwise, it may not be physically realizable system. If a physical system is available, means definitely its mathematical model will have denominator degree will be higher than numerator degree. The transfer function can be represented in two ways. G of s can be represented in two ways. One is called time constant form. Another one is called pole zero form. Time constant form. Another one is called pole zero form. Suppose this is the polynomial, denominator polynomial of second order system. If you find the roots for this, how many roots you will get? 2 roots you will get. Let us call them as z1 and z2. This polynomial can be represented as s plus z1 and s equal to minus z1, s equal to minus z2. These are the 2 roots of this polynomial, z1 minus z1 and minus z2. Therefore, s plus z1 plus s plus z2. If you do this, what you will get? You will get the polynomial, because we are factorizing this polynomial by its roots. So this is, so if you factorize the denominator, you will get like this. So P1, P2, P3, etc., Pn, or Z1, Z2, Z3, etc., Zm. Numerator roots are called Z1, Z2, etc., Zm. Denominator roots are called P1, P2, etc., Pn. If s equal to minus Z1, then you will get S plus Z1, S plus Z2 you will get. Here you are getting the roots are S equal to P1, comma P2, etc. Pn. Therefore, the denominator can be factorized like this. Similarly, numerator polynomial also can be factorized like this. S minus Z1 is Z2, etc. S minus Zm. This, if you factorize and write the transient function like this, then it is called pole zero form, because P1, P2, etc. Pn are roots of denominator. Z1, Z2, Z3, etc. Zm are called roots of numerator. Roots of denominators are called poles. Roots of denominator polynomial are called poles. Roots of numerator polynomial are called zeros. Roots of numerator polynomials are called zeros. Therefore, we are writing in terms of poles and zeros. P1, P2, P3, etc. Pn are poles. Z1, Z2, Z3, etc. Zm are called zeros. If you write in this form, then it is called pole zero form. If you take this P1 out of this polynomial, out of this factor, what you will get? What you will get? Let us take a second order system. P1 S plus P2. Numerator, you are having a K and S plus Z1. This is second order system. Why second order? Two poles are there, that's why second order. Pole zero form. If you take P1 outside, what you will get is K Z1 1 by Z1 S plus 1 whole divided by 1 by P1 S plus P1, sorry, S plus 1 1 by P2 S plus 1. This is 1. So outside you will get P1, P2. Therefore, what are the constants? Now K dash equal to K times Z1 upon P1, P2. That is K dash. Now the K becomes K dash equal to, here you are taking Z1 outside. Here you are taking P1 as well as P2 outside. That's why this becomes like this. Therefore, K dash equal to K Z1 upon P1, P2, or we can say that K dash T Z1 S plus 1 upon TP1 S plus 1 multiplied by TP2 S plus 1. So this 1 by Z1 equal to TZ1. 1 by P1 is equal to TP1. 1 by P2 is called TP2. That's all. This TP1, TP2 are called time constant of the system. TP1, TP2 are called time constant of the system. These are all called time constant. That's why this TP1, TP2, TPN are called time constant of the system. That's why this form is called time constant form. Time constant form. So we can represent the transfer function two ways. One is called a time constant form. That is, S will have coefficient. S will have coefficient plus 1. Pole zero form means S do not have any coefficient. S plus P1, S plus P2, etc. Like that it will be represented. S plane. Already you know what is S plane. S plane is a complex plane. S plane is a complex plane. Complex plane. What is complex plane? The horizontal axis will be sigma. Vertical axis will be j omega. That is called complex plane or S plane, simply called S plane. If you plot the poles, of these systems, plot how to plot here S plus P1. How you find the roots? S equal to minus P1. S equal to minus P2. For that second order example system, the roots of the denominator are minus P1 and minus P2. Or say minus 2, minus 3. Minus 2, minus 3. If you plot in this S plane, minus 2 will be here, minus 3 will be here. So these are all poles of the system. Numerator roots are called zeros. S equal to minus Z1. That is equal to, say, plus 2. Then where it is, it will be mentioned here. It will be mentioned here. This is 0. 0 will be represented by a circle. Poles will be represented by X mark. Poles will be represented by cross mark or X mark. And zeros will be represented by a circle. So here, the poles are in the left hand side, left half plane. This is the right half plane. So there is a significance of location of these poles and zeros that we will see later. But how to plot them like this? The complex plane, you can plot like this. Suppose the poles are S equal to minus P1. Another pole is called minus P2. S equal to minus 2 plus J1. Another pole is minus 3 plus J2. You can plot this. Then plus or minus, minus 2 minus J1. So it must be in complex conjugate only. You cannot write otherwise. So minus 2 plus J1. This pole will be here. This is P1. Minus J. This will be here. P2. So it may be a complex roots also, complex poles also. Here the P1, P2 are called complex poles. Here the poles are real poles. Only real part alone is there. That's why it is called real poles. Similarly, zeros can be a complex or real. That's why you need a complex plane to represent them. S plane or complex plane. The location of these poles are very important. It has significance that we will see later. Already I told you that the order of the system means the order of the differential equation. These two are first order systems. This electrical system is first order system. Because if you write the differential equation for that, it will be a first order differential equation. Let the output be V naught of t, voltage across the capacitor. Input be Vi of t. If you write the differential equation for this Kirchhoff's voltage law, we have to write. The applied voltage is Vi of t equal to, let us assume that current through this circuit is I of t. Therefore, Vi of t equal to Ri plus 1 by C integral of I dt. That's all. Or I can, if I take Laplace transform of this, what you will get? Vi of S equal to Ri of S plus, assuming zero initial conditions, 1 upon Cs, I of S you will get. Let it be 1. What is the output? V naught of S. V naught of t. V naught of t is the output. That is equal to 1 by c integral of I of t dt. I of t dt. If we take Laplace transform, 1 by cs I of s. From this, you can find I of s. I of s equal to cs V naught of s. Cs V naught of s. So let it be second equation. Substitute the value of I of s from the second equation, first equation. What you will get is V I of s equal to V I of s equal to V I of s equal to R plus 1 upon Cs multiplied by I of s equal to Cs V naught of s. If you simplify this, what you will get RCS plus CS getting cancelled. Therefore, RCS plus 1 multiplied by V naught of S. What is output? Output is V naught of S. What is input? VI of S. Therefore, the transfer function is output by input. That is V naught of S upon VI of S equal to 1 upon RCS plus 1. RCS plus 1. What is the order of this differential equation? It is not differential equation. It is integral equation. If you differentiate this once, what you will get? dvi of t by dt or di by dt plus 1 by c I of t. That's all. So it is first order differential equation. First order differential equation. First order differential equation. Therefore, here the degree of s is 1. The degree of s is 1. Therefore, this equation, this system is first order system. First order system. This is also first order system. This is also first order system. What is this system? This is a level system. There is a outflow rate Q naught. There is an inflow rate QI, like your overhead tank, your home. QI, Q naught, QI is outflow rate, QI is inflow rate, liters per hour, liters per minute, like that. Or kg per minute or kg per second, like that. This H is the output. I want to maintain this level H, irrespective of outflow rate. So what I have to do to maintain the level? I have to adjust the inflow rate equal to outflow rate. If you maintain inflow rate equal to outflow rate, level remains constant. So what we have to do? We have to measure the height. If any change in height, if the height decreases, we have to increase the inflow rate. If height increases, we have to decrease inflow rate. That is the idea of control. So like how we are controlling the speed of the car, we are seeing the speedometer. If speed increases, we'll decrease the input. If speed decreases, we'll increase the input. Like that, if level decreases, we'll increase the input. If level increases, we'll decrease the input. That way we can control the level. If you find the mathematical model of this, dH by dt equal to dH by A, dH by dt. A is area of cross section of the tank equal to Qn minus Q naught. This is also first order system. This is also first order system. So this will be represented by output by input. H of s upon input is Qi of s, inflow rate, equal to 1 upon tau s plus 1, k by tau s plus 1. K by tau s plus 1. We do not know the value of k and tau. We do not know the value of k and tau, but anyhow, it is a first order system. So I can simply write k upon tau s plus 1. K upon tau s plus 1 I can write. So this is a first order system. That's why we can represent them k upon tau s plus 1. So first order system means if it is in differential equation, it will be represented like this. Tau dH by dt plus h equal to k qi q in of t. The same is represented in differential equation. If you find the mathematical model of this tank, you will get like this. You will get like this. You will get like this. Now, we know the mathematical model. We know the mathematical model in two forms. One is in differential equation form, another one is transfer function form. Transfer function is from differential equation. Another form of differential equation is transfer function by assuming zero initial conditions. Another form of differential equation is transfer function. By using the transfer function, if you give any input, we can find the output. We can find the time response. What is time response? For a given input, if you draw the output of the system with respect to time, then it is called time response. We can draw the time response for a given system if we know the transfer function of the system. Suppose I know the transfer function of a first order system. Hereafter, I will say first order system. You can assume that it may be a RC circuit, or it may be a level tank, or it may be something. Yeah, some first order system you can assume. A thermometer, you can assume it as a thermometer, first order system. Like that, you can assume. But hereafter, we won't say this is the system, that is the system. We won't say first order system, second order system, third order system, like that we will say. I am taking a first order system whose transfer function is k upon tau s plus 1. K upon tau s plus 1. Its time constant is tau, its gain is k. I'll tell what is k, what is tau, what is time constant, what is gain, I will tell later. K upon tau s plus 1, this is first order system. Or I can write g of s can be written as C of s upon R of s, C of s upon R of s upon k upon tau s plus 1. That way I can write C of s upon R of s equal to k upon tau s plus 1. Tau s plus 1. We can write like this. Suppose I want the response if R of s is an impulse function. R of s is an impulse function. If R of s is an impulse function, then what is the response? Response means output. Response means output. What is the output I want to find? So impulse function, already we know that R of s and R of t, we know the relation. R of t impulse function, del of t, unit impulse function. For that, the Laplace transform of del of t is 1. R of t is u of t, unit step function, u of t. Then its Laplace transform is 1 upon s. If it is a ramp function, R of t, ramp function, then it's Laplace transform 1 upon s square. If it is parabolic function, then it's the Laplace transform 1 upon s cube. Here it is, let us assume that it is an impulse function. Input is an impulse function. Therefore, R of s equal to 1. 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 How to find the response of the system? What is in the left hand side? C of s. If you take Laplace inverse, you will get C of t. Similarly, in the right hand side also, you have to take the Laplace inverse. If you find a Laplace inverse of this, you will get automatically output. So R of t is R of s is 1 and substituted. I have to take Laplace inverse. To find the Laplace inverse, I have to write in this form, s plus whole zero form. To find the Laplace inverse, I have to write in whole zero form. That's why I'm taking tau outside. Therefore, tau multiplied by s plus 1 by tau. 1 becomes 1 by tau. If I take tau outside, therefore, this can be written as k upon tau whole divided by s plus 1 by tau. If we take Laplace inverse of this, what you will get is, if we take Laplace inverse, what you will get is k by tau is constant. 1 upon s plus a. What is Laplace inverse of 1 upon s plus a? E power minus at. E power minus AT you will get. So here, instead of A, it is 1 by tau is there. Therefore, e power minus t by tau you will get. T by tau you will get. So this is the C of t. This is C of t. The time response, impulse response of the system. C of t equal to k upon tau e power minus t by tau. K upon tau multiplied by e power t by tau is the time response in mathematics. We have to plot the response. We have to plot the response. How we can plot the response? We have to vary the t from 0 to infinity. We have to vary t from 0 to infinity and find various values of C of t. Then we can plot. Here it is plotted. Here it is plotted. X-axis is time axis. From 0 to infinity. Y-axis is magnitude. When t equal to 0, when t equal to 0, what you will get? E power minus t by tau. When t equal to 0, e power 0 is 1. You will get k by tau. When t equal to 0, the magnitude is k upon tau. The magnitude is k upon tau. If you give impulse input, the magnitude becomes k by tau. If you substitute t equal to infinity, what is the final value? If t equal to infinity, e power minus infinity equal to 0. E power minus infinity equal to 0. Therefore, the final value is 0. Therefore, it starts from k by 2. Finally, it ends at 0. Exponentially decreases. Exponentially decreases. This is the response. Time response. Time response of first order system for impulse input. For impulse input. This is the time response. This is the time response of the system. What is the waveform of this response? K by tau e power minus t by tau. That is the waveform. K by tau e power minus t by tau is the wave. This is the time response for impulse input. Time response for impulse input. Impulse input. Time response for impulse input. The same first order function, but that step input. R of t equal to u of t. R of t equal to u of t. U of s equal to 1 upon s. 1 upon s. Therefore, C of s upon R of s, that is transfer function equal to k upon first order system. Tau s plus 1. Tau s plus 1. If you substitute R of s equal to 1 by s, what you will get? C of s equal to 1 upon s multiplied by tau s plus 1. K upon s multiplied by tau s plus 1. You will get. Now we have to find Laplace inverse that we do not know. So we have to factorize this. We know Laplace inverse for each factor. That's why let us factorize. That is equal to a upon s plus b upon tau s plus 1. B upon tau s plus 1. A equal to what? A equal to s multiplied by k upon s multiplied by tau s plus 1 at s equal to 0. If you substitute s equal to 0, k, a equal to k. A equal to k. Therefore, similarly, we have to find b also. B equal to tau s plus 1, tau s plus 1, k upon s multiplied by tau s plus 1, where s equal to minus 1 by tau. Minus 1 by tau. S equal to minus 1 by tau. Because tau s plus 1 equal to 0 means s equal to minus 1 by tau. If you substitute, these two are getting cancelled. These two are getting cancelled. S equal to minus 1 by tau. If you substitute, you will get minus k. Here, s equal to 1 minus 1 by tau. If you substitute k tau, you will get. K tau, you will get. So we got A and B values. We got A and B values. A equal to what? K. K upon S plus B equal to minus KT. KT upon K tau upon tau S plus 1. Now we can find the Laplace inverse. K upon S minus. To find the Laplace inverse, we have to write in pole zero form. Therefore, if you take that t outside, you will get S plus 1 by tau. Or you can write K multiplied by 1 upon S minus 1 upon S plus 1 by tau. Now we factorized. C of S equal to C of S equal to C of S equal to K multiplied by 1 upon S minus 1 by S plus 1 by tau. If you find the Laplace inverse, you will get C of t. C of t equal to 1 upon S. It is step. That's why one unit step. 1 minus K multiplied by 1 minus. K is outside. K is outside. Therefore, K multiplied by 1 upon S is 1. Laplace inverse. If you take Laplace inverse for this, you will get e power minus t by tau. Therefore, this is the step response of the first order system. Step response of the first order system. C of t equal to K multiplied by 1 minus e power minus t by tau. To plot this, we have to vary t from 0 to infinity. To plot this, we have to vary t from 0 to infinity. If you substitute t equal to 0, C of 0 equal to what? K multiplied by 1 minus e power 0 equal to 1. That is equal to 0. So it starts at 0. Impulse response where it starts? Starts at K by tau. Impulse response starts at K by tau. Impulse response starts at K by tau. Here, if you see that here, step response starts at 0. C of infinity equal to what? Final value. Final value equal to what? Final value equal to, we have to substitute t equal to infinity. E power minus infinity equal to 0. Therefore, the final value is K. Final value is K. Therefore, finally, it will settle at K. Initially, it will be at 0. Initially, it will be at 0. Therefore, the step response is C of t. Starts at 0, end at K. End at K. So the response will be looking like this. Up to infinity, it remains at K. Final value is K. It remains at K. It remains at K. Here, we can find the definition for time constant. We can find the definition for time constant. The definition for time constant, tau we have seen, in the transfer function tau. The transfer function tau, the definition for this tau is, time taken for step response. Time taken for the step response to reach 63.2% of final value. 63.2% of final value. This is 100%. This is 100%. 100% is what? K. K is the 100%. Finally, where it reaches? At kth value, it reaches. At kth value, it reaches finally. But initially, it is 0. Gradually, it increases. Finally, it reaches K value. While reaching, sometime it will be at 63.2% of final value. 63.2% of final value. At the time taken to reach this point, is called time constant tau of this system. This is called tau. The time taken, say 5 seconds means the transfer function can be written as K upon tau 5s plus 1. I can write K upon 5s plus 1 because tau equal to 5. How I got tau value? Time taken to reach 63.2% of final value for a step input. That is very important. We have to mention the step. Time taken to reach 63.2% of final value for step input. For step input, time taken to reach 63.2% of final value is time constant. If you know that is equal to 5 seconds, then the transfer function can be written as k upon 5s plus 1. So for different system, the time constant will be different. What is the definition for time constant? Time taken for the step response of a system to reach 63.2% of final value is known as time constant of the system. Time constant of the system. Time taken for the step response of the system to reach 63.2% of final value. So in this, for this system, it is 5 seconds. For this system, it is 5 seconds. For this system, it is 5 seconds. 5 seconds. Some other system, it may quickly raises to final value. For that system, the time taken is 3 seconds, 2 seconds. Some other system, further quickly it reaches final value. It is 0.5. 0.5. It takes only 0.5 seconds to reach 63.2% of final value. The first system takes only 0.5 seconds to reach 63.2% of final value. Second system takes 2 seconds to reach 63.2% of final value. Third system takes 5 seconds to reach 63.2% of final value. Which is faster? The first system, which takes only 5.5 seconds to reach 63.2% of final value. Therefore, the time constant, this system is fast system. Then this system, this is slow system. This is slowest system. This is slower system. This is fast system. Because the time constant is 0.5. For this time constant is 2. For this time constant is 5. As time constant increases, the system becomes slow. The system becomes slow. By looking at the transfer function of first order system, we can say that how the system behaves. If time constant is large, means it takes long time to settle. Takes long time to settle. If time constant is very small, means it quickly settles. Fast system. It quickly settles. Fast system. So, what is C of t? We derived C of t equal to k multiplied by 1 minus e power minus t by tau. Am I correct or not? This is the response we got. This is the response we got. If you substitute t equal to tau, that is time constant tau. If you substitute t equal to tau, what you will get? K into multiplied by 1 minus e power minus 1. Am I correct or not? 1 minus e power minus 1 equal to 0.632. 1 minus e power minus 1 equal to, this part is equal to 0.632. It means what? The time, from this we got the definition. That is 0.632 times is, you will get C of tau, you will get. When t equal to tau, you will get the output is equal to 0.632 times k. K is the final value. K is the final value. If you change k, what will happen? If k equal to 5, in this case, for all the system, I am having 3 systems. One is, this is third system, k upon 5s plus 1. Second system, k upon 2s plus 1. Third system, k upon 0.5s plus 1. Sorry. The first system is k upon 0.5s plus 1, which is fast system. This is the fastest system because time constant is 0.5. Slowest system, this is because time constant is 5 seconds. Slower system, this is 2s. By looking at time constant, we can say that this is fastest. But in all the 3 cases, k equal to 5, That's why all settled at 5. K equal to 5. K equal to 5. That's why all settled at 5. Finally, it reaches 5 because K equal to 5. The K is called static gain of the system. K is called static gain of the system. K is called static gain of the system. Or simply gain. We can call it as simply gain. But it should be in time constant form. It should not be in pole zero form. The K is correct when it is in time constant form. That we can understand from here. Here, what I said, while writing pole zero form, I wrote K dash. K dash. While writing pole zero form, while writing pole zero form, it is written as K dash. While writing in time constant form, it is written as K. K is not equal to K dash because K dash equal to what? K dash equal to K multiplied by Z1 upon tau 1, tau 2 for second order system. K is multiplied by Z1 divided by tau 1, tau 2. That is equal to K dash. Therefore, K is not equal to K dash. If pole zero form means K is not correct. Time constant form means K is correct. Time constant form is time constant form means K is correct value of K. You will get correct value of static gain. You will get correct value of static gain. You will get. You understand this point? So this K means this K is this K is in time constant form. Time constant form. It means what? It means what? The final value will be at K. The final value will be at K. If instead of 5, suppose I'm here, I'm having 5, here I'm having 3, here I'm having 10 means where the first response will settle at 10, second response will settle at 3, the third response will settle at 5. Here all K values are equal. That's why all settled at 5. I think now you understand the difference between static gain and time constant. Static gain and time constant. In the previous class, we have seen impulse and step responses of first order system. Today, let us see the step response of second order underdamped system. Second order system will be represented by second order differential equation. D square y by dt square, where y of y is the output. X is the input. If we take Laplace transform, assuming 0 initial conditions, then we will get y of s upon x of s. So how you will get 1 upon omega n square s square assuming 0 initial condition, y of s plus 2 zeta omega n s y of s. Again 0 initial condition, y of s equal to k x of s. If you find y of s upon x of s equal to k upon omega n square s square plus 2 zeta omega n s plus 1. If you multiply the numerator denominator by omega n square, you will get k omega n square upon s square plus 2 zeta omega n plus omega n square, where omega n is natural frequency of the system. where omega n is the natural frequency of the system. Where omega n is the natural frequency of the system. This form is called natural frequency form. Natural frequency form. This form is called time constant form. The constant term must be 1. The constant term must be 1, where tau square equal to 1 upon omega n square. The coefficient of s square is tau square. The time constant square. The time constant equal to tau equal to 1 by omega n. That is the relation between natural frequency and the time constant. This form is called natural frequency form for second order system. We'll use this form to find the step response of the system. Step response means what is input here is x of s, output is y of s. Here we are assuming that x of s equal to step input, that is 1 upon s, or x of t equal to u of t, that is step input. What is step input? Step input will be like this. Magnitude is unit step input. This is the step input to this system. For that, what is the response? Y of t we have to find. The second order system, if you see RLC circuit, already we have seen that RC circuit is first order system. RC circuit. If you take an RLC circuit, R, L, and C, then it is second order system. If you write the KCL, Kirchhoff's voltage law, what is that? V I of t equal to R I of t plus L di by dt, 1 upon C, integral of 0 to t, I of t, not tau, I of t dt. Okay, tau is correct because limit is 0 to tau is correct. Dummy variable is tau. If we didn't put this t here, then we can put t there. Okay, this is Kirchhoff's voltage law. By using Kirchhoff's voltage law, we got this. This is integral differential equation. If you differentiate once, d v I of t upon dt equal to R di by dt plus L d square I upon dt square plus I of t upon C. So it is a second order differential equation. So it is a second order system. Second order system. Similarly, a mass, a single mass, any mass is there, automatically it becomes second order system. As number of masses increases, the order will increase. So d square x of t by dt square, d x by dt x of t. So second derivative is there, therefore this is second order system. Second order system. These are all examples for second order system. But here we won't consider the system. Simply we'll take a second order system and we will find the step response. That we will see now. Example for second order systems are this mass spring dashboard system or RLC circuit. RLC circuit. These are the examples for second order system. Now let us find the unit step response of second order system, whose transfer function is represented in natural frequency form, omega n square, k equal to 1, s square plus 2 zeta omega n s plus omega n square, and k equal to 1. If you consider, you will get y of s upon x of s equal to the second order in natural frequency form. Here, let us assume that x of s is a step input, unit step input, that is 1 upon s. Therefore, this becomes omega n square upon s multiplied by s square plus 2 zeta omega n s plus omega n square. Here we are assuming that zeta is less than 1. There are three possibilities for the roots. Maybe the complex roots, the roots may be real, complex, repeated roots, or imaginary roots. There are four possibilities. Here we are considering only one possibility, that is based on zeta. That also we'll see. Then before doing that, if you do this partial fraction, what you will get is S1 and S2 are roots. What are the roots for second order system? S1, one root, another root is S2, that is equal to minus B. Here B equal to 2 zeta omega n plus or minus square root of B square. This is B. 4 zeta square omega n square minus 4 AC. A equal to 1. 4 A equal to 1. C is omega n square upon 2A. Here A equal to 1. Therefore, 2. That's all. 2 getting cancelled. 2 getting cancelled. 2 getting cancelled. Therefore, this can be written as minus zeta omega n plus or minus omega n square can be taken outside. Omega n square root of zeta square minus 1. What is the assumption we made? Zeta is less than 1. Therefore, this quantity is negative always. Zeta is less than 1. That's why this quantity is negative always. If zeta is less than 1, the root is complex. The root will be complex conjugate. Zeta is assumed as less than 1. If zeta equal to 1, what will happen? This second part becomes 0. That's why roots will be real and repeated roots. If zeta equal to 1, repeated roots will get. If zeta is greater than 1, if zeta is greater than 1, always this is positive. That's why roots are real, always real only. Real but not repeated, variable. 2 real roots you will get. If zeta equal to 0, what you will get? Zeta equal to 0 means first part becomes 0. First part becomes 0. Second part is 0 means you will get always you will get negative value. Minus 1 is I. Therefore, you will get plus or minus j omega n you will get. Only imaginary part. Zeta equal to 0. So how the responses will be for zeta equal to 1, zeta greater than 1, zeta equal to 0, that we will see later. Similarly, for zeta less than 1 also, you will get a different response. Now we are going to see only zeta less than 1. The other three we'll see later, we'll see. Now we will consider zeta less than 1. That's why less than 1 means always this is negative. That's why if you take minus 1 outside, what you will get? Zeta omega n plus or minus j. If you take minus 1 outside, it becomes j omega n square root of 1 minus zeta square, because I am taking minus 1 outside. 1 minus zeta square. If you take multiply both minus 1, because you are taking minus 1 outside, so minus 1 becomes j. So it is a complex root always. Complex root always. This is the root. S1 and S2 are equal to this. For this, we have to find the response. For this, we have to find the response. So here, what are the roots? Roots are already we found that S1 and S2 equal to, we factorized the second part. We factorized the second part. That's why we can write S plus S1 multiplied by S minus S plus S2. That's what in the previous slide. S plus S1 and S plus S2. Because this minus sign can be absorbed. So we can put like this. Now we have to do the partial fraction. So that's why we are writing A upon S, Bs plus C. Why Bs plus C? It is a second order polynomial, a second degree polynomial. That's why we have to write Bs plus C, that you know. So S square plus 2 zeta omega n S plus omega n square. So if we have to find B and C, we have to find. So what we can do is, we have to find B and C. For that, what we can do is A multiplied by A upon S plus this statement, Bs plus C upon S square plus 2 zeta omega n S plus omega n square equal to omega n square upon S multiplied by S square plus 2 zeta omega n S plus omega n square. If you do the cross multiplication, you will get this equation. If you do the cross multiplication, for this S getting cancelled, A multiplied by S square plus 2 zeta omega n S plus omega n square, plus here S will be there. That's why S multiplied by Bs plus C equal to omega n square. Compare the coefficient of S square. Coefficient of S squares are compared, then A plus B equal to 0. A plus B equal to 0. You got one equation. If you compare coefficient of S, here the coefficient of S is 2 zeta omega n S. Here the coefficient of S is C. That's why 2 zeta omega n S, 2 zeta omega n A plus C equal to 0. We got two equations. Now we have to find A. A can be easily found. A from here we can find A. A equal to what? A equal to S multiplied by omega n square upon S multiplied by S square plus 2 zeta omega n S plus omega n square, where S equal to 0. This is getting cancelled. If we put S equal to 0, A equal to 1. A equal to omega n square upon omega n square equal to 1. So A equal to 1 we got. Now we have to find A equal to 1 means B equal to minus 1, because A plus B equal to 0. C equal to A equal to 1, therefore C equal to minus 2 zeta omega n. A equal to 1, therefore C equal to minus 2 zeta omega n. Substitute all these values here. 1 upon S, because A equal to 1. B also equal to 1, therefore S plus C equal to 2 zeta omega n minus 2 zeta omega n. Therefore, here you will get a minus sign. Sorry. Here you will get the minus sign. S plus 2 zeta omega n 1. Now we are why I explained this, because if zeta is less than 1, what happens to the roots? That's why I explained this. To find the response, no need to find the roots. No need to find the roots. Why I found the roots here? Because there are 4 possibilities. If zeta is less than 1, the roots are complex. If zeta, what is the assumption we made? Zeta is less than 1. Therefore, the roots are complex. Roots are complex. That's why Bs plus C. That's why Bs plus C. And if zeta equal to 1, repeated roots. If zeta is greater than 1, real. If zeta equal to 0, it is an imaginary root. To explain that, I find the roots here. To find the response, no need to find the roots. Here, we are separating this into 2 parts. One is 2 zeta omega n S. So we can write this as zeta plus, S plus zeta omega n whole square. That is equal to what? S square plus 2 zeta omega n s plus zeta square omega n square. So the first two terms are here. First two terms here. The first two terms are here. What is the terms missing? Zeta square omega n square is missing. That's why we have to add and subtract this term so that we can write s plus zeta omega n whole square plus here what is the term? Zeta square omega n square. That has to be subtracted. So add one term and subtract one term minus zeta square omega n square. Up to this becomes s plus zeta omega n whole square. These three terms becomes s plus zeta omega n whole square. And what is the remaining? Remaining terms are omega n square minus zeta square omega n square. If you take omega n square outside, what you will get? 1 minus zeta square. 1 minus zeta square you will get. So now omega n square 1 minus zeta square can be assumed as omega d. That can be assumed as omega d. Therefore, the equation becomes s plus 2 zeta omega n upon s plus zeta omega n whole square plus omega d square. Why we wrote this step is, while finding Laplace inverse, it will be easy. That's why we are writing like that. Sometimes in mathematics, we will write deliberately some steps. Here also, we are deliberately writing this step to make Laplace inverse simple. Laplace inverse simple. That's all. So now we can separate this into two terms. Instead of single term, I want to separate this into two terms. Again, it is also to make Laplace inverse simple. So 2 zeta omega n, s plus 2 zeta omega n. If you take this zeta omega n, you will get one more term like this. One more term like this. That's all. Up to this, just manipulation. Just manipulation. Now, we have to manipulate this to make it convenient while taking Laplace inverse. You see that what is, instead of omega n, it must be omega d. Then only we can write it as a cos term. So omega d is not there. That's why we'll take this step. Omega d equal to what? Omega d equal to omega n square root of 1 minus zeta square. Therefore, this omega n can be replaced by omega d upon square root of 1 minus zeta square. You substitute here, you will get this term. Zeta also taken outside. Zeta divided by square root of 1 minus zeta square. Omega d upon s plus zeta omega n whole square plus omega d square. Now, omega d assumed as a means a upon s square plus a square term is there. That's all. Instead of, if in a function, instead of s, if s plus a is there, s plus b, let us assume that s plus b. Here I am writing that Laplace inverse of, instead of s, I am having s plus b upon s plus b square, s plus b square plus a square. If it is there, then Laplace inverse is equal to e power minus bt, that is c of t equal to, the response equal to c of t equal to, or y of t equal to 1 minus 1 by s becomes 1 minus. Instead of s, we are having s plus b. That's why e power minus zeta omega t, omega nt. Here it must be omega nt. Omega nt cos omega dt minus zeta upon 1 minus zeta square e power minus omega nt sin omega dt. That's all. The formula is written here. Laplace inverse of s plus a. What I wrote there is, but instead of a, b is there. Instead of b, is okay. Now we know that we'll take a triangle. We'll take a triangle. Here the angle is phi. Here this is square root of 1 minus zeta square. The length of this side is square root of 1 minus zeta square. Square of it, this side is zeta. So what is hypotenuse? Sum of squares of these two. If you add these two, you will get 1 minus zeta square plus zeta square. That is equal to 1. Therefore, hypotenuse is 1. Therefore, sine phi can be written as square root of 1 minus zeta square upon 1. Similarly, cos phi equal to adjacent side upon hypotenuse zeta. Therefore, tan phi equal to opposite side upon adjacent side. So we can replace this by now we cannot replace. Now we have to simplify. One more step we have to write. C of t equal to, we can take this e power minus zeta omega nt outside. Therefore, we can write 1 minus e power minus zeta omega nt. And I want to take that 1 by square root of 1 minus zeta square also outside. That's why I'm getting 1 minus zeta square also outside. That's why that is missing here. That's why it should be multiplied by square root of 1 minus zeta square cos omega dt minus is taken outside. That's why plus. So here zeta only there. Therefore, e power minus zeta omega nt is taken outside. This is also taken outside. Only zeta is there. Therefore, we can write sine omega dt. Sine omega dt we can write. So now we can write 1 minus e power minus zeta omega nt upon 1 minus zeta square. This is equal to what? This is equal to what? Sine phi. So we can write, instead of this, we can write sine phi. Sine phi. We can write as such cos omega dt plus, instead of zeta, we can write cos phi. Cos phi sine omega dt. That's all. So it is equal to sine a plus b. Sine a plus b. That's why we can, this can be replaced by sine a plus b. Sine a plus b. Therefore, 1 minus e power minus zeta omega nt upon square root of 1 minus zeta square sine a plus b omega dt plus phi. That's all. Where phi equal to tan phi equal to what? Square root of 1 minus zeta square by zeta. Therefore, phi equal to tan inverse of square root of 1 minus zeta square upon zeta. This is the response. What is the response? This is the response. This is the response we derived. 1 minus e power minus zeta omega nt upon square root of 1 minus zeta square sine omega dt plus phi. Sine omega dt plus phi. You should memorize this. Often it will be useful. Often it will be useful. That's why you have to memorize this. This is the response for second order underdamped system. Second order underdamped system. What is the response? The response, if you see, if you put t equal to 0, here also t equal to 0, sine phi you will get, if you put t equal to 0, this becomes 1, t equal to 0, this becomes 1, sine omega, this also sine phi equal to square root of 1 minus zeta square, these two getting cancelled, the entire term becomes 1. When t equal to 0, this entire term becomes 1. So 1 minus 1, 0. So the response will start at t 0. Response will start at 0. So response will start at 0. Where it will end, we have to substitute in t equal to infinity. If you put t equal to infinity, e power minus infinity equal to 0. The entire term becomes 0. Therefore, it is equal to 1. So it will settle at 1. We do not know whether it will go like this or go like this or it go like this. We do not know. We do not. To find that, we have to substitute various values for t and we have to find. So for that, if you substitute various values for that, we'll get the response will be looking like this. Follow my pen. It will follow like this. If you substitute various values, it will follow like this. So this response is when zeta is less than 1. After some time, it will settle. It will oscillate. After some time, it will be like this. So after this, it is steady state response. Before that, what is the transient response? Before that, it is called transient response. The transient part depends upon zeta. If zeta is greater than 1, the response will be like this. The derivation will be different. Because roots are different. If zeta equal to 1, repeated roots, smartest, zeta equal to 1. Zeta is less than 1, it starts oscillating. Overshoot is coming. Overshoot means it goes above the final value. If it goes above the final value, then it is called overshoot. This part is called overshoot. This part is called overshoot. The blue line. Overshoot. If zeta is less than 1, it has overshoot. Zeta is less than 1, it has overshoot. If zeta is 0, it always oscillates. If zeta is 0, the response will be like this. Constant amplitude. If amplitude decreases, finally it will settle. Amplitude is not decreasing. The constant amplitude up to infinity, it is oscillating. So this is zeta equal to 0. This response is zeta equal to 0. Zeta is less than 1, it oscillates and settles. Zeta is equal to 1, smartest response. If zeta is greater than 1, sluggish response. Zeta is greater than 1, sluggish response. This is the example. Zeta equal to 2. It is plotted for zeta equal to 2. After some time, you'll see all these simulations you can see in MATLAB. I will explain. I will demonstrate some programs. You can try at your home. After this unit, we will simulate all this in MATLAB. And this is a MATLAB simulation. Just you have to substitute value of zeta and you have to run. That's all. It will give the response. It will give the response. You can check. That we'll see later. In one class, we will see the simulations. MATLAB simulations. If zeta equal to 0, we'll get sustained oscillation. This is called sustained oscillation. Oscillation is remains there, sustained. This is called sustained oscillation. Sustained oscillation. Zeta less than 1, damped oscillation. That is called damped oscillation. Zeta equal to 1, smartest, that is called critically damped. If zeta equal to 1, that is called critically damped oscillation. If zeta is greater than 1, over damped oscillation. Or sluggish response. So we can by using damping, we can say over damped, critically damped, under damped, sustained oscillation, undamped. So we can, by using damp, we can say the 4 responses: over damped, critically damped, under damped, undamped. No damping. Damping means amplitude decreasing. No damping. That's why undamped response. So we can say that over damped, under damped, critically damped, and undamped. 4 responses we have seen. Now we'll see this when zeta equal to 0, undamped response. Zeta equal to 1, critically damped. Critically damped response. If zeta less than 1, under damped response. It means it oscillates and settles. Zeta greater than 1, over damped response. So there are 4 types of response. It depends upon zeta. All the 4 we have seen. Undamped means continuous oscillation without any decrease in amplitude. Zeta equal to 1 means critically damped. Smartest response. Underdamped means it has oscillation and settles. Overdamped means that is greater than 1 means it takes long time to settle. Long time to settle. That's all. Now we can specify the response. That is called time domain specifications. Time domain specifications. Already I told you that the response, if it goes beyond the final value, then it is called overshoot. Overshoot. This part is called overshoot. This part is called overshoot. The amplitude of this overshoot is called peak overshoot. Peak overshoot. MP. That is called peak overshoot. Peak overshoot. Time taken to reach the first time final value. Time taken to reach first time final value. Here it reaches first time final value is called TR raise time. TR raise time. It is the time taken required to reach the final value. This is the final value. Finally, it settled here. This is the final value. It settled here. And finally, it settled here. So, the time taken to reach first time final value. First time, but it is not remains there. But it oscillates. But the time taken to reach first time final value is called TR. This is the TR value. This is TR. Time taken to reach the final value. First time. MP already I told you. Peak overshoot. The amplitude of amplitude, maximum amplitude. It exceeds the final value. Then time taken to reach this maximum value is called TP, peak time. This is called what? Peak time. At this time, it will reach the maximum value. Always TP is greater than TR. Because after reaching TR only it can reach TP. Therefore, TP is greater than TR. TP is peak time at which the maximum value will occur. The maximum amplitude will occur at TP. Maximum overshoot is MP. Maximum overshoot is MP. Maximum overshoot is MP. Settling time. Another definition is settling time. Another time domain specification is settling time. Where it settles final value. That is called settling time. We can tell some tolerance because it never settles at practical system never settles at 1. It will oscillate around 1. It will oscillate around 1. This oscillation is called noise. Noise. Noise always will be there. Noise always will be there. Why? Noise always will be there. Noise always will be there. How noise is generated in electronic system? We see that what is Ohm's law? Ohm's law? At constant temperature. At constant, very good. At constant temperature, I is proportional to V. or Ri equal to V, where R is constant if temperature is constant. Otherwise, R will vary. R will vary as T varies. Therefore, what is the room temperature now? Say 26, maybe 26, around 26. Can I say 26? I can't say because we are breathing. Our temperature is 37. So the temperature is oscillates around 26. We are saying that 26. If we measure, the measuring device will oscillate like this, about 26. That is called noise. Why? Because the measuring device has some resistance. The resistance is in room temperature. Room temperature oscillates around 26. That's why the output voltage will never indicate 26 degree. It will oscillate like this. So all electronic device will have noise. How noise is generated? Because of temperature. Temperature is not 26. It oscillates around 26. It vibrates like this. I mean, say like that. It vibrates about 26. Because of that vibration, the voltage also vibrates. The output voltage also vibrates. Wherever you have electronic system, noise is inevitable. Noise is inevitable because natural. Because natural, the temperature never be constant. Never be constant. That's why it is inevitable. That's why this output never be at 1 because electronics is involved here. That's why it never be at 1. If it is pure mechanical system, we can keep at 1. Even mechanical system also will vibrate. There are many reasons. We are not going to see all those things. But anyhow, it vibrates about its final value. That is noise. That noise, because of that noise, we are taking some tolerance. Tolerance means, say I am taking 2% tolerance. If it oscillates with about 2% within, that is between 98% and 102%, I am saying that it is settled. I am saying that it is settled. So after this point, the tolerance is 0.2%. That is 2%. The tolerance is, it varies from 98 to 2%. That's why after this, we can say that it is steady state response. Before that, we can say that it is transient response. Transient response. Before this, it is transient response. After this, it is steady state response. We are ignoring that 2% variation. We are ignoring that 2% variation. Therefore, settling time is, this is TS, settling time. After this point, it is within that 2%. It oscillates, but within that 2%. Therefore, this point is called settling time. Settling time, TS. Time taken to reach this point is called settling time. Time taken to reach this point is called settling time. You understand this point? So, raise time is time taken to reach first time final value. Peak time is the time at which the maximum overshoot happens, maximum magnitude happens. Maximum overshoot means the amplitude of this maximum overshoot, that is MP. Settling time is time taken to reach the final value with a tolerance of 2% and remains within the 2%. Then that is settling time. TK ratio is, its amplitude is decreasing. Its amplitude is, the overshoot is decreasing. At what rate it decreases? It decreases. Suppose here the amplitude is B, overshoot is B. Here the overshoot is A, means B by A is called TK ratio. It decreases at this rate, we can say. It decreases at the rate of B by A. And the second overshoot is B, first overshoot is A. So it decreases at this rate. We can say B by A. The ratio between second overshoot and first overshoot is called TK ratio. TK ratio. the afternoon, we'll see the derivations for all these time domain specifications. In the previous class, we have seen time response for second order underdamped system. Now we will see the time domain specifications for second order underdamped system. Here we are having the response for second order underdamped system. The first time domain specification is raise time, TR. TR means the time taken to reach first time final value. That is TR. So it reaches first time final value at this point. At this point. Therefore, time taken to reach this point is TR. But by definition, it takes time from 10% to 90%. Also, we can say like that. But while calculating, we'll take from t equal to 0 to time taken to reach 100%. TP is, this is overshoot. It goes beyond the final value and then return back and oscillates. So this part, this is overshoot. This part is, follow my pun, this part is overshoot. Time taken to reach this maximum value is called TP, peak time. This is peak time. This time is TP. The time at which the maximum value is reached, that is called TP. The magnitude above final value is called peak overshoot. And the TS is settling time. TS is settling time, time taken to reach 98 to 102% of final steady state value and remains there. Already I told you that tolerance is required. The tolerance is 2% means from 98% to 102%. If it is within that oscillation, but the tolerance with the 2% oscillation means we are assuming that it is settled. So at this point, it reaches within the 2% tolerance. Therefore, the time taken to reach this point is TS. So up to this point, it is called transient response. After this, it is called steady state response. So we have seen peak time, maximum overshoot MP, and then settling time also we have seen. Decay ratio. Decay ratio means the first peak is the magnitude above final value is A. The second peak, the magnitude above steady state value is B. That B by A is called decay ratio. The ratio at the speed at which it decreases. We are telling in terms of decay ratio, B by A. That's all. These are all time domain specifications. We'll derive the expression for each expression. First, let us derive time domain specification of raise time, TR. What is the definition for TR? Time taken to reach first time final steady state value. What is the magnitude at that point? CT equal to 1. What is the expression for response? Second order response for step input, second order underdamped system. Zeta is less than 1. For that, what is the response? Already we derived C of t equal to 1 minus e power minus zeta omega n t upon square root of 1 minus zeta square sine omega dt plus 5. For zeta less than 1. Here, when it reaches first time, when it reaches first time steady state value, that is final steady state value, this is TR. TR, first time when it reaches, the magnitude is 1. Therefore, we can substitute C of t equal to 1. If you substitute C of t equal to 1, these two ones are getting cancelled. Therefore, this part is equal to 0. that is e power minus zeta omega n t upon square root of 1 minus zeta square sine omega dt plus phi equal to 0. Why this is equal to 0? Because at this point, the value of c of t equal to 1. If you substitute that, 1 getting cancelled, therefore this part is equal to 0. But at what time this value we entered? A t equal to tr. That's why wherever you find t, it becomes tr. E power minus zeta omega n tr upon square root of 1 minus zeta square sine omega dtr plus phi equal to 0. That we got. This is the magnitude of sine signal. Am I correct or not? Suppose I'm having a sine signal whose magnitude is 5 means, whose magnitude is 5 means, this is its magnitude is 5. How we will write 5 sine omega t? We'll write like this. This 5 indicates that the magnitude, amplitude of this signal. Therefore, here sine omega dtr plus phi, for that the magnitude is e power zeta omega n tr upon square root of 1 minus zeta square. The sine signal always oscillates. Even at infinity, it oscillates. Even at infinity, it oscillates. It never becomes rest. Sine signal always oscillates. Sinusoidal signal will become 0 at some interval. Sinusoidal signal becomes 0 at some interval. At this point, it becomes 0. At this point, it becomes 0. At this point, it becomes 0. So, but this is not equal to 0. At this instant, this is not equal to 0. Am I correct or not? At this instant, the magnitude is not equal to 0. The magnitude is not equal to 0. Therefore, this is not equal to 0 and this is equal to 0. Why? This periodically it becomes 0. At this point, this becomes 0. That's why the right hand side becomes 0. Therefore, sine omega d tr plus phi equal to 0. At this moment, the sine wave equal to 0. That's why right hand side we got 0, because this is not equal to 0. The magnitude is not equal to 0. The sinusoidal signal, periodically it becomes 0. At this instant, this becomes 0. Therefore, sine omega dtr plus phi equal to 0. And this is not equal to 0. The magnitude is not equal to 0. Therefore, sine omega dtr plus phi equal to 0. Sine theta equal to 0 means theta equal to 0 or n pi, we can say theta equal to n pi, 0 or n pi. So here it is not 0 because after some time, that's why it must be equal to n pi. Omega d tr plus phi equal to n pi. At every instant, this is n equal to 1. At this instant becomes 0. Here n equal to 2, it becomes 0. Again n equal to 3, it becomes 0. At n equal to 4, it becomes 0. Like that. So at n pi, this omega dtr equal to n pi. That's why it becomes 0. Or this tr is first time it reaches 0. First time it reaches 0. Therefore, n equal to 1. We can write... Therefore, we can write omega dtr plus phi equal to pi. Why? When n equal to 1, it becomes 0. Or tr equal to omega dtr plus phi equal to pi. Therefore, we can write tr equal to pi minus phi divided by omega d. But omega d equal to what? Omega n multiplied by square root of 1 minus zeta square. Therefore, tr equal to pi minus phi upon omega n square root of 1 minus zeta square. Square root of 1 minus zeta square. Square root of 1 minus zeta square. That's all. Therefore, the expression for tr, time at which it reaches first time peak, is pi minus phi upon omega n square root of 1 minus zeta square. This phi equal to tan inverse of square root of 1 minus zeta square upon zeta in radians. Its unit is in radians. Peak time. Peak time. Rise time we have seen. Now let us see peak time. Peak time is what? The waveform it goes over first overshoot and second overshoot, third overshoot, like that it goes. Peak time means first the maximum amplitude occurs, that is TP, peak time. We have to find this TP. To find a peak, what is the slope at this point? What is the slope at TP? Slope at TP is, what is slope at TP? Slope means what? Tangent. Slope means tangent at that point. If you draw a tangent at this point, it will be a horizontal line. Am I correct or not? If you draw a tangent at this point, it will be a horizontal line. What is the slope of that horizontal line? 0. Slope of that horizontal line is 0. Therefore, slope at TP equal to 0. Simply we can say that slope at TP equal to 0. How to find the slope at TP? What we have to do is, we know the expression for C of t equal to 1 minus e power minus zeta omega n t upon square root of 1 minus zeta square multiplied by sine omega dt plus phi. This is the expression for C of t. How to find the slope at TP? Replace, differentiate this. If you want to find the slope at any point, we have to differentiate this and equate to 0. Why we are equating to 0? Tangent equal to 0. When the waveform turns, it means what? Either it will be at maximum or at minimum. Both are possible. That's why in mathematics, if we equate to 0, you will get either maximum or minimum. To find whether it is maximum or minimum, we will find the second derivative, it must be negative. Derivative of derivative will find if it is negative, then it is maximum. If you see the second derivative at this point, you will get negative slope. At this point, you will get positive slope, because after that it will increase. After that it will increase. That's why you will get positive slope. Here, after that it will decrease. That's why you will get negative slope. That's why second derivative becomes negative at this point. Okay. But we know that here we'll get the positive value. That's why we are not finding the second derivative. We'll find the first derivative of this equation. What is the first derivative of this equation? C of t equal to 1 minus. If you differentiate 1, what you will get? 0. That's why it is not mentioned here. 0 minus, what is that? E power minus zeta omega nt upon square root of 1 minus zeta square. We wrote as such. We wrote that as such. Then if you differentiate sine omega dt plus phi, what you will get? Cos omega dt plus phi. If you differentiate this omega dtp, you will get omega d. That's why we wrote here. So product function, derivative of AB. So we differentiate cos omega dtp plus phi. We got differentiation of sine omega dtp multiplied by omega d minus. Now we have to keep this as such. Sine omega dt plus tp, sine omega dtp plus phi, we are keeping as such, and differentiating this part, e power minus zeta omega and tp. We differentiate that. What is the coefficient of tp? Minus zeta omega n upon square root of 1 minus zeta square. If you differentiate exponential function, you'll get the same. That's why we are writing e power minus zeta omega n tp. That's all. Why t is replaced by tp? We are finding differentiation at t equal to tp. That's why all t is replaced by tp. At that point, what is the slope? Slope is 0. That's why equated to 0. Now, common terms will be taken out. E power minus zeta omega nt in both terms are there. That's why we are taking that outside. we are taking that e power minus zeta omega n tp outside. This square root of 1 minus zeta square also in both terms, that is also taken outside. Here cos, this is minus, that's why we are putting minus sign here. Cos omega d tp plus phi multiplied by omega d. Multiplied omega d equal to what? Omega d equal to omega n square root of 1 minus zeta square. So instead of omega d, we can write omega n square root of 1 minus zeta square plus sine omega d tp plus phi multiplied by zeta omega n. This minus sign becomes plus. This becomes plus. Okay. Okay. This becomes plus because of 2 minus sign, it becomes plus sine omega d tp plus phi zeta omega n equal to 0. Again, at this point, the magnitude is not equal to 0. The magnitude is not equal to 0, and this can be, this omega n also can be taken outside. In both terms, we have omega n. That's why omega n also can be taken outside. The omega n also can be taken outside. So what you will get? This is negative, this is positive. That's why you will write this first zeta sine omega d tp plus phi minus square root of 1 minus zeta square cos omega d tp plus phi. But this is not equal to 0. The magnitude is not equal to 0. But sine term, periodically it becomes 0. At this instant, this periodical function is 0. Therefore, we can write zeta sine omega d tp plus phi minus square root of 1 minus zeta square cos omega d tp plus phi equal to 0. This periodical function is equal to 0. If we equate this equal to 0, we can substitute zeta equal to what? Already we have one expression. This is phi. This is equal to square root of 1 minus zeta square, and this is zeta, and this is equal to 1. Therefore, zeta can be written as cos phi. Zeta can be written as square root of 1 minus zeta square can be written as sine phi. If you substitute this here, this zeta becomes cos phi, and the square root of 1 minus zeta square becomes sine phi equal to 0. So this is what? Sine A cos B plus cos A sine B. Therefore, sine A plus B. Sorry, minus sign is here. Therefore, sine A minus B. Here B is phi. Therefore, A is omega d tp plus phi minus phi. Phi getting cancelled. Therefore, sine omega d tp equal to 0. Sine omega d tp equal to 0. But that means omega d tp equal to either 0 or 1 pi or 2 pi, etc. This is happening at the first time. Therefore, we can equate this equal to pi as we have seen in the previous derivation. Omega d tp equal to pi. Therefore, tp equal to pi upon omega d. Or we can say that pi upon omega d can be written as omega n square root of 1 minus zeta square. Tp equal to pi upon omega n square root of 1 minus zeta square. Time taken to reach the peak value is pi upon omega n square root of 1 minus zeta square. This is second derivation. These are all useful to solve sums. That's why you have to memorize all these derivations. The formula has to be remembered. TR equal to what? Pi minus pi upon omega d. Here, Tp equal to what? Pi by omega d. So you can easily remember. Tp equal to what? Pi minus pi upon omega d. Maximum offshoot, MP. This is the waveform we got. This is MP. This magnitude is MP. It occurs at what point? TP. Therefore, CT equal to C of t equal to MP. C of 1 minus C of t equal to MP. T equal to TP. At t equal to TP, it is MP. At this point, what is the time? Time is TP. If you substitute t equal to TP and subtract from 1 because its magnitude is 1, which is bigger? C of t, because it is overshoot. That's why C of t is bigger. That's why we'll write C of TP minus 1 equal to M. C of TP minus 1 equal to M. What is C of TP? We know that C of t equal to 1 minus e power minus zeta omega n t upon square root of 1 minus zeta square sin omega dt plus 5. So here, wherever you find t, substitute TP and replace C of TP by this. So what you will get? What you will get? C of TP is replaced by this 1 minus e power minus zeta omega n t upon square root of 1 minus zeta square sin omega dtp, because at this point we are finding TP plus 5 minus 1, because we are subtracting minus 1, equal to MP. This is MP. 1 getting cancelled. 1 getting cancelled. 1 getting cancelled. So we are having e power minus zeta omega n TP upon square root of 1 minus zeta square sin omega d TP plus 5. This we have to find. But we know the value of TP. We can substitute the value of TP. If you substitute here the value of TP, what you will get? E power minus zeta omega n TP equal to 5 by omega d, that is omega n square root of 1 minus zeta square. I am substituting TP upon square root of 1 minus zeta square sin omega t. TP equal to what? 5 by omega t plus 5 equal to MP. The minus sign is there still. So omega d getting cancelled here. Here omega n getting cancelled. Omega n getting cancelled. So we can write sin pi plus 5 is there. Sin pi plus 5. This can be written as MP equal to e power minus zeta omega n pi by omega d. Omega n getting cancelled. MP equal to omega n getting cancelled. E power minus zeta pi upon square root of 1 minus zeta square upon 1 minus zeta square. This sin omega d, here also omega d getting cancelled. That's why we can write sin pi plus 5. That can be written as sin a plus b. Sin a cos b plus cos a sin b. Sin pi equal to 0. Therefore, this term becomes 0. Cos pi equal to minus 1. Cos pi equal to minus 1. Therefore, this minus sign is getting cancelled now and it becomes positive. So, MP equal to e power minus zeta pi upon square root of 1 minus zeta square, and sin pi equal to what? This sin pi equal to square root of 1 minus zeta square. Already we derived. If you substitute that, the denominators square root of 1 minus zeta square and sin pi getting cancelled, because sin pi equal to square root of 1 minus zeta square. Therefore, MP equal to e power minus zeta pi square root of 1 minus zeta square. MP equal to e power minus zeta pi upon square root of 1 minus zeta square. If you want, it will be a factor. Here, this is 1 means This will be about 0.6 or 0.4 like that. It will be a factor. If you want to represent them, what 0.6 is, what is the percentage of 60%. So to represent in percentage MP equal to 100 times e power minus zeta pi upon square root of 1 minus zeta square. Sometimes it will be asked in percentage. That's why we have to multiply this by percentage. That's all. That's all. So MP equal to this MP equal to e power minus zeta pi upon square root of 1 minus zeta square, or percentage MP equal to 100 times e power zeta pi upon square root of 1 minus zeta square. Settling time. From this point onwards, it is within the tolerance of 2%. Morning we have seen that what is tolerance. Noise is inevitable. That's why always it will oscillate around the final value. That's why 2% is taken as tolerance. So after this, it oscillates, but the maximum oscillation is only within that plus or minus 2%. So after this, it is steady state. Before this, it is transient. Now we have to find the time Ts. We have to find settling time. This point is called settling time. This point is called settling time. We have to find the Ts. Here C of t equal to what? We have to understand from C of t. C of t equal to 1 minus e power minus zeta omega n t upon square root of 1 minus zeta square sine omega dt plus 5. This is the expression for C of t. Here, let us assume that finally it settles at 1. It means what? This part becomes 0. This part becomes 0. This part becomes 0 always. Earlier, what we have seen that at this point, the sinusoidal function is 0. At this point, sinusoidal function is 0. At this point, the sinusoidal function is 0. We are assuming like that. At this omega dt plus phi is 0. At this point, like that here, at this point, omega, like that we have derived. But here, the entire part becomes 0. The entire part becomes 0. Then only it will settle at 1. The entire part is not settled at 1. Instead, it is equal to plus or minus 2% or plus or minus 0.02. 2% is 0.02. So this entire magnitude is equal to 0.02. This sinusoidal function always it oscillates. So it oscillates, but its magnitude is 0.02. Therefore, this part must be equal to 0.02. This part must be equal to 0.02. Then only within that 0.02, less than or equal to 0.02. Therefore, we are taking that part alone and equate to 0.02. To find Ts, we are equating this part. Why? Because the C of t becomes 1 means, because settled at 1, let us assume that no noise is settled means this part must be equal to 0. But we are assuming that it is not settled because of noise. It oscillates around 1. Its amplitude is 2. Therefore, the second part is equal to 0.02 plus or minus 0.02. Therefore, you will get value from plus 0.98 to 1.02 because of this tolerance, plus 0.02 or minus 0.02. So its value. Therefore, this value is equal to 0.02. But the sinusoidal value always not equal to 0. Periodically, it becomes 0, not always 0. That's why its amplitude is decided by this. That's why this part is taken and equate to 0.02. If you bring this square root of 1 minus zeta square to the right hand side, you'll get this. Take ln on both sides. If you take ln, the exponential becomes e minus zeta omega n ts. Why I put ts? Because at settling time, that's why ts, e power minus zeta omega n ts. Right hand side, we have to take ln logarithmic, natural logarithm. That's why ln of 0.02 square root of 1 minus zeta square. Therefore, ts equal to minus ln of 0.02 square root of 1 minus zeta square upon zeta omega n. The right hand side value for different values of zeta, as zeta varies from 0 to 0.9, above 0 to 0.9, it value varies from 3.91 to 4.74. It value varies from 3.91 to 4.74. It value varies from 3.91 to 4.74. Let us approximate this to 4. Approximate this to 4. Then you will get Ts equal to 4 upon the numerator value varies from 3.91 to 4.74. Therefore, 4 upon zeta omega n. Therefore, settling time is 4 upon zeta omega n. Settling time Ts equal to approximately equal to 4 upon zeta omega n, because the numerator value varies from 3.91 to 4.74. As zeta varies from above 0 to below 0.9, its value varies from 3.91 to 4.74. So in that case, this can be approximated to 4 upon zeta omega n. If you consider a tolerance of 5%, it means what? Plus or minus 0.055%. If you consider tolerance, the numerator approximate value is 3. Therefore, Ts equal to 3 upon zeta omega n. In the examination, they may ask for 5% tolerance means you have to consider this formula. 2% tolerance means you have to consider this formula. This is for 2% tolerance. This is for 5% tolerance. So time taken to reach the settling time, the time taken to reach the settling point, Ts equal to 4 upon zeta omega n or 3 upon zeta omega n. That's all. We'll see the examples tomorrow. Yesterday we have seen time domain specifications. Today let us see some sums on time domain specifications. Obtain the unit step response and the unit impulse response of the following system. What is the system given? C of S upon. This is the system given. He didn't mention about closed loop, open loop. While seeing control system sum, you should be very careful about the statement open loop, closed loop. Here it doesn't mean that anything. Only thing is we apply these two inputs to this system. That's all. That's why we need not bother. Simply take this and compare with the standard one. Obtain the unit step response and the unit impulse response of the following system. We have to compare with the standard system. If you compare with the standard system, omega n square, in place of omega n square, 10 is there. Therefore, omega n equal to root 10. Omega n equal to root 10. In place of 2 zeta omega n, yes. Yes is missing. 2 zeta omega n, yes. 2 is there. Therefore, 2 zeta omega n equal to 2. 2 getting cancelled. Omega n equal to root 10. Therefore, zeta equal to 1 upon root 10. Zeta equal to 1 upon root 10. Zeta is less than 1. We have to compare We have to compare with the standard transfer function. What is standard transfer function? Omega n square upon s square plus 2 zeta omega n s plus omega n square. If we compare these two, omega n is root 10, zeta equal to 1 upon root 10. From this, we can understand that zeta is less than 1. From this comparison, we can understand that zeta is less than 1. Therefore, we can directly use the derived formula. What is the derived formula? C of t equal to 1 minus e power minus zeta omega n t upon square root of 1 minus zeta square sine omega n t omega dt. Omega dt plus 5. This is the formula we derived for underdamped system. This is also underdamped system, zeta less than 1. Therefore, we can directly apply the formula. 1 minus e power minus zeta omega n. If you multiply omega n and zeta, it becomes 1. Zeta omega n equal to 1. Here we got, in this step, zeta omega n equal to 1. Therefore, e power minus t, zeta omega n equal to 1. Upon square root of 1 minus zeta square. Zeta is 1 by root 10. If you square that 1 by 10, you will get square root of 1 minus 1 by 10 sine omega n. Omega d equal to what? Omega d equal to omega n square root of 1 minus zeta square. So if you substitute that root 10 for omega n, square root of 1 minus 1 by 10 zeta square 1 by 10 multiplied by t. Multiplied by t. Plus 5. But phi equal to what? Tan inverse of, phi equal to tan inverse of 1 minus zeta square upon zeta. Zeta equal to 1 by root 10. So if you substitute, phi equal to 71.736. Tan inverse of square root of 1 minus 1 by 10 zeta square 1 minus zeta square 1 by root 1 by 10 whole divided by 1 upon root 10. If you find tan inverse, you will get 71.736. So we can substitute for pi. We can substitute for pi 71.736. So we got the response. E power minus t is, we keep as such. 1 by square root of 1 minus 1 by 10 is 1.053. So we got the response. What response? Step response. We know the formula, from that we obtained the step response. Because the question is obtained. Sometimes they will ask, derive the unit step response. You have to see the question. Sometimes 8 marks question, they will simply ask, derive the step response. For the given system means you have to derive up to this step. Up to C of t, you have to derive, then substitute the values. For a unit impulse response, impulse input, what is the response? Impulse, what is the impulse input means? R of s equal to 1. Impulse input means R of s equal to 1. So C of s, if you bring that R of s here, R of s equal to 1. So we got this. Now we have to find the impulse response. So we can, we have to see the roots, not equal roots, distinct roots. That's why we can write these two can be combined. S plus 1 whole square, if you write, you will get 2s. Therefore, we will write s plus 1 whole square. What is the extra term? Extra term is 1. So 1 we have to subtract from that. That's why this becomes 9. So this step we can write like this. S square plus 2s plus 1 plus 9. This can be written as s plus 1 whole square plus 3 square. So that is written here. Wherever you find S, S is S plus 1. S is S plus 1. What is the formula? This is the formula, Laplace inverse. B upon S plus A whole square plus B square equal to e power minus AT, because instead of S, S plus A is there. That's why we have to include that e power minus AT sin BT. Sin BT. So we can write instead of 3 here, 10 is there. That's why numerator, what we have to write is, the numerator we have to write 3.33 multiplied by 3 upon S plus 1 whole square plus 3 square. So for this part, we can find the response. Instead of S, S plus 1 is there. Therefore, if we take Laplace inverse, what you will get? E power minus t sin 3t you will get. Therefore, 3.3 is there. That is written here. So the response is C of t equal to 3.3 e power minus t sin 3t. That's all. So find, obtain the unit step and unit impulse response. We obtained both. Yesterday we have seen time domain specifications. Today let us see some sums on time domain specifications. The parameters of mechanical system of figure are M equal to 100 kg. M is given. M is 100 kg. F equal to 1000 Newton per meter per second. F is given. Already I told you that B or F can be used to represent friction coefficient or dashpot coefficient. The dashpot coefficient B or F. K equal to 10,000 Newton per meter. K is given. The step force F of t of 100 Newton is applied. F of t equal to 100 Newton. This is equal to 100 Newton is applied. So the mass at t equal to 0. At t equal to 0, this force is applied. Initial conditions, the displacement is y. The initial condition y of 0, that is initial displacement is 0. Initial velocity also 0. That is given. From the physical parameters of the system, obtain the transfer function model parameters. Obtain transfer function model parameters. Damping ratio, undamped natural frequency omega n, damped natural frequency omega d. Also obtain the step response. Hence, sketch the response. From the physical parameters of the system, obtain the transfer function model. So we have to obtain differential equation. Then we have to convert the differential equation into transfer function model. Then we have to find zeta. We have to find zeta. Then we have to find omega n, natural frequency, omega d, undamped natural frequency. Finally, obtain the step response and sketch the response. Rough. response. We have to sketch. That's all. So we have to obtain the mathematical model. You know how to obtain the mathematical model. Here the displacement is y. Therefore, m d square y upon dt square plus f dy by dt plus ky equal to applied force f of t. If you find the Laplace transform by assuming zero initial conditions are zero given already. Therefore, m s square y of s plus f s y of s plus k y of s equal to f of s. F of s is input, y of s is output. Therefore, we can write m s square plus f s plus k y of s equal to f of s. Therefore, the transfer function Laplace transform of output, that is y of s, upon Laplace transform of input f of s equal to 1 upon m s square plus f s plus k. Now we have to substitute the given values. M equal to 100 kg. If you substitute, what you will get? 1 upon 100 s square plus f equal to 1000 s plus k equal to 10,000. That's all. The applied force f of t is 100 newtons. That is given. A step force of f of t is given. Step force. Now, we have to write this in natural frequency form. This is in time constant, neither in the time constant form nor in the natural frequency form. Natural frequency form means coefficient of s square must be 1. Time constant form means constant term must be 1. Time constant form means constant term must be 1. Natural frequency form means coefficient of s square must be 1. But neither time constant form nor natural frequency form. Let us take 100 outside. 1 by 100. 0.01. 1 by 100. 100 I am taking outside. Therefore, s square plus, if we divide this by 100, you will get 10s plus 100. We got the transfer function. That is also equal to 0.01. 1 by 100 is 0.01 upon s square plus 10s plus 100. Now we can find zeta, omega n and omega d. Omega n equal to omega n square equal to 100. Therefore, this implies omega n equal to 10. We got one answer. If you compare with the standard transfer function, what is standard transfer function? Omega n square, k omega n square upon s square plus 2 zeta omega n s plus omega n square. Omega n square equal to 100. That's why we got omega n equal to 10. 2 zeta omega n equal to 10. 2 zeta omega n equal to 10. But omega n equal to 10, therefore 20, zeta equal to 10 divided by 20, that is equal to 0.5. Zeta equal to 0.5. That is also we got. Now we have to find omega d. Omega d equal to what? Omega d equal to omega n square root of 1 minus zeta square. That is equal to omega n is 10 square root of 1 minus 0.5 square. 1 minus 0.5 square. What's the value? 8.6. Okay. 8.67. 8.67. So omega D equal to 8.67. Omega D equal to 8.67. Zeta equal to 0.5. Omega n equal to 10. We got all the three answers. Obtain the step response for given input. Input equal to 100 newtons. Input equal to 100 newtons. What is the transfer function? Given transfer function y of s upon f of s equal to 0.01 upon s square plus 10s plus 100. Therefore, y of s equal to this is 100 damped system. This is 100 damped system, and f of s equal to what? F of s equal to 100 is given. F of t equal to 100 given. F of t equal to 100. Therefore, f of s equal to 100 upon s. If you take Laplace transform of a constant, 100 is a constant. Because it is given as step force. Step force means up to infinity. Step force means constant value up to infinity. That's why it is a constant value if you take Laplace transform 100 by s. So if you substitute that, what we will get is 0.01 multiplied by 100. Y of s equal multiplied by 100. F of s equal to 100 by s. S multiplied by s square 10s plus 100. Here zeta equal to 0.5. 100 damped system. Zeta less than 1. Omega n equal to what? Omega n equal to 10. Omega d equal to 8.66. So we know that for 100 damped system, C of t equal to what? 1 minus e power minus zeta omega n t upon square root of 1 minus zeta square sine omega dt plus 5. So if you can substitute all these values. 1 minus zeta equal to 0.5 multiplied by omega n 10, 5 e power minus 5t upon square root of 1 minus zeta square, 1 minus 0.5 square sine omega d 8.67 t plus 5, where 5 equal to tan inverse of square root of 1 minus 0.5 square upon 0.5. That is equal to pi by 3. 60 degree. If you find using calci, you will get 60 degree. 60 degree. That's why we can write pi by 3 or 60 degree as you wish, or you can write 60 degree. So this is equal to e power minus 5t 1 by square root of 1 minus 0.5 square, that is equal to 2 by root 3. 2 by root 3, or you can write the fractional value. Find 1 by square root of 1 minus 0.5 whole square equal to how much? You find 2 by root 3 how much? You find 1 by square root of 1 minus 0.5 square. So 0.01 is outside. 1 minus e power minus 5t sine 8.67 t plus 60 degree. What is this? 1 upon square root of 1 minus 0.5 square, how much? One point one 1.15. We can write like this. Finally, hence sketch the response. Hence sketch the response. We have to draw the response. It is underdamped system, therefore the response will be looking like this. What is the final value? Where it will settle? The crucial point is what is the final value at mention. Final value at mention. Here 0.01 is there. We have taken outside. Here substitute t equal to infinity. E power minus 5 infinity equal to 0. This part becomes 0. This part becomes 0. Therefore, finally, it will settle at 0.01. You can draw this, underdamped system, you will draw. But if you didn't mention that 0.01 here, they will not give mark. How I got that? In the final response, substitute t equal to infinity. If you substitute t equal to infinity, what you will get? This becomes 0. This entire term becomes 0. Only 1 will be there. So, final value is 0.01. Therefore, in the graph, you have to mention that 0.01. The final steady state value is 0.01. That's all. Yesterday, we have seen time domain specifications. Today, let us see some sums on time domain specifications. Next sum. A unity feedback system is characterized by an open loop transfer function. Open loop transfer function. Determine the gain K so that the system will have a damping ratio of 0.5. For this value of K, determine the settling time, peak overshoot, time to peak overshoot for a unit step input. These are all asked. So determine the gain K so that the system will have a damping ratio. So zeta equal to 0.5. It is given. The open loop transfer function G of S is given. That is equal to K upon S multiplied by S plus 10. This is a unity feedback system. It means it is a closed loop system. But given is open loop transfer function. Given is open loop transfer function. You know the seventh rule. Actually, what is given is K upon S multiplied by S plus 10 is given. This is given. For this system, you have to find K so that the system will have a damping ratio zeta of 0.5. It means what? We have to apply seventh rule. If you apply seventh rule, what you will get? Because the given transfer function is open loop transfer function. That you should note. In always, you should note this. While solving second chapter, particularly second chapter. All other chapters, you can directly use open loop transfer function. In second chapter only, we should read the question carefully. Open loop transfer function is given. That's why we have to find the closed loop transfer function. S multiplied by S plus 10. Seventh rule we are applying. Negative feedback. Unity feedback system means negative feedback. It is obvious. 1 plus K upon S multiplied by S plus 10. Therefore, what we will get is K upon S multiplied by S plus 10. If we take LCM, instead of 1, you would write S multiplied by S plus 10 plus K upon S multiplied by S plus 10. This is these two getting cancelled. Therefore, K upon S square plus 10S plus K. Finally, you will get the closed loop transfer function is K upon S square plus 10S plus K. (10S plus K). This is closed loop transfer function. That is C of S upon R of S is given. Determine K so that the system will have a damping ratio of 0.5. Zeta is given. Zeta is given. Zeta equal to 0.5 is given. If you compare this with the given transfer function is compared with the standard transfer function, omega n square upon S square plus 2 zeta omega n s plus omega n square equal to K upon S square plus 10S plus K. Now what we will get is 2 zeta omega n equal to 10, that is given. Zeta equal to 0.5, that is also given. Therefore 2 omega n equal to 2 omega n equal to 0.5, that is 1 by 2. These two getting cancelled. Therefore omega n equal to 10. Omega n equal to 10. Since zeta equal to, this implies 2 1 by 2 omega n equal to 10. Therefore omega n equal to 10. Therefore K equal to 10. Omega n square equal to 10. Determine the settling time. Therefore omega n square equal to 10. Omega natural frequency is 10. Therefore K equal to 10. Determine K. K equal to 10. That is one answer. Omega n equal to root 10. Omega n equal to root 10. Determine the settling time. TS. TS, settling time. TS equal to what? For 2% tolerance. Let us find for 2% tolerance. 2% tolerance, TS equal to 4 upon zeta omega n. That is equal to 4 divided by 0.5 multiplied by root 10 equal to how much? Settling time. Sorry. Omega n equal to 10. Therefore, omega n square equal to 100. So here we got omega n only. Omega n equal to 10. Therefore, omega n square equal to 100. Therefore, K equal to 100. K is omega n square. K equal to omega n square. Omega n square and K are equal. Therefore, K equal to 100. Here, 10. Therefore, 4 by 5 equal to 0.8 seconds. 0.8 seconds. TS, settling time. Peak overshoot, MP. Percentage peak overshoot. Percentage peak overshoot, MP equal to e power minus zeta pi upon square root of 1 minus zeta square multiplied by 100. That is equal to 100 multiplied by e power minus zeta is 0.5 multiplied by pi upon square root of 1 minus 0.5 square. What is the overshoot? Percentage overshoot? Percentage overshoot is 16.3%. 16.3%. Time to peak overshoot, TP. TP equal to pi upon omega d or omega n square root of 1 minus zeta square. Pi upon omega n equal to 10 square root of 1 minus zeta square, that is 0.5 square. Point 5 square. Equal to TP equal to what? Formula is pi upon omega n square root of 1 minus zeta square. Point 362 seconds. 0.362 seconds. That's all. Yesterday we have seen time domain specifications. Today let us see some sums on time domain specifications. Next sum. A unity feedback system is characterized by an open loop transfer function. Open loop transfer function. Determine the gain K so that the system will have a damping ratio of 0.5. For this value of K, determine the settling time, peak overshoot, time to peak overshoot for a unit step input. These are all asked. So determine the gain K so that the system will have a damping ratio. So zeta equal to 0.5. It is given. The open loop transfer function G of S is given. That is equal to K upon S multiplied by S plus 10. This is a unity feedback system. It means it is a closed loop system. But given is open loop transfer function. Given is open loop transfer function. You know the seventh rule. Actually, what is given is K upon S multiplied by S plus 10 is given. This is given. For this system, you have to find K so that the system will have a damping ratio zeta of 0.5. It means what? We have to apply seventh rule. If you apply seventh rule, what you will get? Because the given transfer function is open loop transfer function. That you should note. In always, you should note this. While solving second chapter, particularly second chapter. All other chapters, you can directly use open loop transfer function. In second chapter only, we should read the question carefully. Open loop transfer function is given. That's why we have to find the closed loop transfer function. S multiplied by S plus 10. Seventh rule we are applying. Negative feedback. Unity feedback system means negative feedback. It is obvious. 1 plus K upon S multiplied by S plus 10. Therefore, what we will get is K upon S multiplied by S plus 10 we take LCM, instead of 1, you would write S multiplied by S plus 10 plus K upon S multiplied by S plus 10. These two getting cancelled. Therefore, K upon S square plus 10S plus K. Finally, you will get the closed loop transfer function is K upon S square plus 10S plus K. Ten S plus K. This is closed loop transfer function. That is C of S upon R of S is given. Determine K so that the system will have a damping ratio of 0.5. Zeta is given. Zeta is given. Zeta equal to 0.5 is given. If you compare this with the given transfer function is compared with the standard transfer function, omega n square upon S square plus 2 zeta omega n S plus omega n square equal to K upon S square plus 10S plus K. Now, what we will get is 2 zeta omega n equal to 10. That is given. Zeta equal to 0.5. That is also given. Therefore, 2 omega n equal to 2 omega n equal to 0.5. That is 1 by 2. These two getting cancelled. Therefore, omega n equal to 10. Omega n equal to 10. Since zeta equal to, this implies 2 1 by 2 omega n equal to 10. Therefore, omega n equal to 10. Therefore, K equal to 10. Sorry. Omega n equal to 10. Therefore, omega n square equal to 100. So here we got omega n only. Omega n equal to 10. Therefore, omega n square equal to 100. Therefore, K equal to 100. K is omega n square. K equal to omega n square. Omega n square and K are equal. Therefore, K equal to 100. Settling time. TS. Settling time. TS equal to what? For 2% tolerance. Let us find for 2% tolerance. 2% tolerance. TS equal to 4 upon zeta omega n. That is equal to 4 divided by 0.5. Here 10. Therefore, 4 by 5 equal to 0.8 seconds. 0.8 seconds. TS. Settling time. Peak overshoot. MP. Percentage peak overshoot. Percentage peak overshoot. MP equal to e power minus zeta pi upon square root of 1 minus zeta square multiplied by 100. That is equal to 100 multiplied by e power minus zeta is 0.5 multiplied by pi upon square root of 1 minus 0.5 square. What is overshoot? Percentage overshoot. Percentage overshoot is 16.3%. 16.3%. Time to peak overshoot. TP. TP equal to pi upon omega d or omega n square root of 1 minus zeta square. Pi upon omega n equal to 10 square root of 1 minus zeta square, that is 0.5 square. 0.5 square. Equal to TP equal to what? Formula is pi upon omega n square root of 1 minus zeta square. Point 362 seconds. 0.362 seconds. That's all. Already we have seen time response of second order underdamped system. Then we have seen time domain specifications. Based on that, we are going to see some problems. A second order mechanical system is represented by the transfer function theta of s upon I of s equal to 1 upon a step input of 10 Newton meter is applied to the system and the results are given below. The maximum overshoot is 6%. Maximum overshoot is 6%. MP. MP equal to what? 6%. Therefore, 100 e power minus zeta pi upon square root of 1 minus zeta square. That is equal to 6%. Time at peak overshoot, TP, equal to 1 second. TP, what is the formula? What is the formula? Pi upon omega n square root of 1 minus zeta square. That is equal to 1 second. Steady state value of the output. Theta steady state. Steady state value of the output equal to 0.5 radians. It means second order mechanical system. We do not know the nature of the system, whether it is underdamped, overdamped, critically damped, undamped. It is not undamped because it is settled at 0.5. Therefore, any one of these three categories, overdamped, underdamped, critically damped, it is settled somewhere. Let us assume that it is underdamped, it is settled somewhere. That value is 0.5. That is given. Finally, it is settled at 0.5. The steady state value of the output is 0.5 radians. This is given here. Determine the value of J, F and K. Determine the value of J, F and K. First, it is given that MP equal to, that is 100 e power minus zeta pi upon square root of 1 minus zeta square equal to 6. From that, we can find zeta. So, this can also be written as e power minus zeta pi upon square root of 1 minus zeta square equal to 0.06 or minus zeta pi upon square root of 1 minus zeta square equal to ln of 0.06. So now we have to find zeta square. What is the value of this? Equal to minus 2.8134. So both the minus signs getting cancelled. Therefore, zeta square pi square upon 1 minus zeta square equal to 2.8134 whole square. Find zeta. Point 667. Zeta equal to 0.667. This implies zeta square pi square equal to 2.8134 whole square minus zeta square 2.8134 whole square. From this we can find zeta. Zeta equal to 0.67. Therefore, underdamped, what we have assumed is correct. Underdamped system. Underdamped system. Then time at the peak overshoot TP equal to TP equal to 1 second. That is this is first part. The second part is pi upon omega n square root of 1 minus zeta square equal to 1. Already we know the value of zeta. Therefore, we can find omega n. Omega n equal to pi upon square root of 1 minus zeta square. We know zeta, 0.667. Find omega n. Find omega n. $4.217. 4.217 omega n. Now we have to compare steady state value. Steady state value theta SS equal to 0.5, that is given. For what? Input 10 newtons per second. It is given that theta of S upon I of S equal to 1 upon J square S square plus Fs plus K. I of S is given. I of S equal to what? I of S equal to 10 upon S. Because step input means if you take Laplace transform for that step input 10 upon S you will get. Therefore, I of S equal to 10 upon S. If you substitute this here, what you will get is theta of S equal to 10 upon S multiplied by J square S square plus Fs plus K. That is theta. We have to find the final value. We know the final value theorem. What is final value theorem? You studied in signals and systems. J. Yes. Thank you. J. Final value theorem states that y of infinity equal to, or we can write like this. limit t tends to infinity, y of t equal to, we can say y of infinity also. Limit t tends to infinity, y of t equal to, that is the final value, equal to limit s tends to 0, s y of s. If you know y of s, we can find y of infinity, that is equal to y of infinity. Here I am using caps y in s domain. In time domain, I am using small y. We can find y of infinity by using this final value theorem. So here we know theta of s. Theta steady state means equal to limit t tends to infinity, theta of t, that is equal to limit s tends to 0, s theta of s, by using final value theorem. Limit t tends to infinity, theta of t equal to limit s tends to 0, s theta of s. That is final value theorem. So if you apply that final value theorem here, we will get theta of infinity. Theta of infinity equal to limit s tends to 0, s multiplied by 10 upon s js square plus fs plus k. These two getting cancelled. S getting cancelled. If you substitute s equal to 0 here, what you will get? 10 upon k you will get. This is given. The value is given. What is that? Steady state value is 0.5 radians. It is given. Therefore, 10 by k equal to 0.5. 10 by k equal to 0.5. Theta of infinity equal to limit s tends to 0, s theta of s. Theta of s equal to what? 10 upon s js square fs plus k. S getting cancelled. If you substitute s equal to 0, s equal to 0, this becomes 0 and this also becomes 0. Therefore, it is equal to 10 upon k. That is given. What is the value given? 0.5. That is 1 by 2. Therefore, k equal to 20. 10 upon k equal to 1 by 2. Therefore, k equal to 20. Now we got one answer. Find the value of k is asked. Find the value of k is asked. We found only we have to find the j and f we have to find. Determine the values of j, f and k. One unknown, that is k is we found. K we found. J and f we have to find. To find j and f, compare this transfer function with the standard one. Compare this transfer function with the standard one. What is standard transfer function? Omega n square upon s square plus 2 zeta omega n s plus omega n square equal to, what is given? 1 upon j s square plus f s plus k. Therefore, coefficient of s square must be 1. Here, coefficient of s square is not equal to 1. Therefore, we have to rewrite this as 1 by j whole divided by s square plus f upon j s plus k by j. Omega n square equal to k upon j. Omega n square equal to k upon j. One equation we got. 2 zeta omega n. 2 zeta omega n equal to f. F. Therefore, f by j f by j. 2 zeta omega n equal to f by j. Therefore, we know zeta. We know zeta. This is second equation. This is second equation. That's all. From these two, already we know one value. Two equations we have, two unknowns we can find. Number of unknowns and number of equations are equal means we can find. Now, what is k? What is the value of k? K equal to 20. Therefore, we can substitute k value, zeta value. Whether we know zeta value 0.667. That is also we know. If we substitute that, we'll get J and F. We can find J and F. Find J and F. Because we know that K equal to 20 and zeta equal to 0.667. That we know. So find F and J. Omega n also we know, Sorry. What we found here, omega n. Omega n equal to 4.217. So these two we know, omega n we know, zeta we know. So we can find KJF. K by J equal to omega n square, that is 4.217 whole square. That is equal to that is equal to 20 by J, because K also we know 20. Therefore, J equal to 1.124. J equal to 1.124. F by J equal to 2 zeta omega n. 2 into 0.667 and omega n equal to 4.217. Therefore, J also we know, F upon J equal to 1.124 equal to 2 into 0.667 multiplied by 4.217. Therefore, F equal to 6.323 Newton per meter per second. This is a dashpot point constant B equal to 6.323 Nm Newton per meter per second. Already we have seen time response of second order underdamped system. Then we have seen time domain specifications. Based on that, we are going to see some problems. Consider the unit step response. Consider the unit step response. It means what? Input R of S equal to 1 upon S. G of S is given. Unit step response. Therefore, the input is 1 upon S. Of a unity feedback system. So it is closed loop system, closed loop feedback system, whose open loop transfer function is G of S is given. That is 1 upon S multiplied by S plus 1 is given. But there is the system is closed loop. The given system is open loop transfer function. Therefore, closed loop transfer function T of S equal to G of S upon 1 plus G of S, H of S. Here, H of S equal to 1. Why I said 1 H of S equal to 1? Why h of s equal to 1? Here it is given that unity feedback system. Indirectly, they are saying that it is h of s equal to 1. Unity feedback system means, suppose I am having a system R of s. This is G of s. This is given. What is given? 1 upon s multiplied by s plus 1. This is given. This is C of s, output. The feedback is unity feedback system. Here 1, the transfer function of h of s equal to 1. Unity feedback system. Always in control system, they didn't mention about feedback. You have to take negative feedback only, unless otherwise specified. If they said positive feedback, then only you have to take positive feedback. Otherwise, you have to take negative feedback only. So unity feedback system means unity negative feedback system. So this is minus. Therefore, the formula is 1 plus. The formula is 1 plus. Why 1 plus? Because negative feedback. Unity feedback, that's why h of s equal to 1. Therefore, the transfer function T of s equal to G of s upon 1 plus G of s. Hereafter, we need not write h of s if it is a unity feedback system, because h of s equal to 1. If it is a unity feedback system, no need to write h of s. Directly, we can write G of s upon 1 plus G of s, we can write. This is for unity feedback system. What is H? G of s? G of s is given 1 upon s multiplied by s plus 1 whole divided by 1 plus 1 upon s multiplied by s plus 1. S plus 1. Therefore, if we take LCM, what you will get? 1 upon s multiplied by s plus 1 whole divided by s multiplied by s plus 1 plus 1 whole divided by upon s multiplied by s plus 1. These two getting cancelled. Therefore, T of s. Therefore, T of s, the given transfer function is 1 upon s multiplied by s plus 1 plus 1. That is equal to 1 upon s square plus s plus 1. S square plus s plus 1. That is given. That's all. These steps you have to do. Why we have to do all these things? TFS is not given. Closed loop transfer function is not given. Open loop transfer function GFS is given. That's why we have to find TFS, then we have to proceed the sum. If we directly use this, you will get wrong answers. This is open loop. This is open loop transfer function. We have to find closed loop transfer function using 7th rule. Now we have to compare this with the standard transfer function. What is standard transfer function? Omega n square upon s square plus 2 zeta omega n s plus omega n square. Here coefficient of s square is 1. Here also coefficient of s square is 1. Therefore, we can compare the other things. Omega n square equal to 1. Therefore, omega n equal to 1. 2 zeta omega n equal to 1. Therefore, zeta equal to, if you substitute omega n equal to 1, you will get zeta equal to 1 by 2. That is equal to 0.5. Omega n equal to 1. What is the final answer? Find peak time, maximum overshoot, settling time for 2% tolerance. These are all asked. These are all asked. The first question is peak time. TP. TP equal to peak time equal to pi upon omega n square square root of 1 minus zeta square. That is equal to pi upon omega n square is 1 square root of 1 minus 0.5 square. Find 3.62 seconds. Maximum overshoot, MP is asked. Race time also asked, I didn't notice. We'll see. Maximum overshoot, MP. MP equal to what? Formula. Percentage. If you want to tell in terms of percentage, 100 e power minus zeta pi upon square root of 1 minus zeta square equal to 100 e power minus 0.5 multiplied by pi square root of 1 minus 0.5 square equal to MP equal to how much? 16.3%. Then we have to find settling time. Settling time, TS. Settling time for 2% tolerance. 2% tolerance equal to 2% tolerance equal to 4 upon zeta omega n. That is equal to 4 upon 0.5 omega n equal to 1. That is equal to 8 seconds. 8 seconds. Now we have to find race time. TR. Race time means what? Suppose this is the response means. This is the response means. This is the final value. This is TR. Race time. TR. This is TP. This is TP. Peak time. This overshoot in percentage of final value is MP. This is settling time, TS, 2% tolerance. So TR we have to find. TR equal to what? Pi minus pi upon omega n square root of 1 minus zeta square. You have to find pi in terms of radians mode. Put the calcium radians mode and then find. Phi equal to what? Tan inverse of square root of 1 minus zeta square upon zeta. That is equal to square root of 1 minus 0.5 square divided by 0.5. Tan inverse of find arctan. TR equal to pi minus tan inverse of 1 minus zeta square upon zeta. That is equal to 60 degree. But we should not write 60 degree because it should be written here in radiant mode. That is very, very important. You should not find in degree mode. Pi by 3 you will get. So you substitute, you will get 2.42 seconds. 2.4. They got check whether it got 2.42 seconds. Got 2.42 seconds. Already we have seen time response of second order 100 amp system. Then we have seen time domain specifications. Based on that, we are going to see some problems. Consider the closed loop transfer function given by. Closed loop transfer function is given. T of S is given. Determine the value of zeta and omega n so that the system responds to a step input with approximately 5% overshoot with a settling time, approximately 5% overshoot with a settling time of 2 seconds. Settling time of 2 seconds. Settling time of 2 seconds. Overshoot. We have to find omega n and zeta. These are the two unknowns here. Omega n and zeta are the two unknowns. Zeta equal to what? Omega n equal to what? We have to find. 5% overshoot. MP equal to what? Percentage MP equal to 100 e power minus zeta pi upon square root of 1 minus zeta square. That is equal to 5 given. If you substitute, automatically you will get zeta. Find zeta. So what you will get? E power minus zeta pi upon square root of 1 minus zeta square equal to 0.05 or minus zeta pi upon square root of 1 minus zeta square equal to ln of 0.05. You will get negative value. That's why negative sign will getting cancelled. ln of squaring on both sides and finally find zeta. Zeta equal to what? 9. Same value, 0.69. In the previous sum, we got 0.6678. Here, 0.69. Zeta equal to 0.69. And another settling time is given. TS equal to, let us assume that it is 2% tolerance. Tolerance is not given. If it is not specified, we have to take 2%. So 4 upon zeta omega n equal to 2 seconds. Omega n equal to 4 upon 2 zeta equal to omega n. Omega n equal to 2.896. So here it is directly the closed loop transfer function is given. Sometimes instead of asking like this, they will ask, write the transfer function and find the unknown parameters in the transfer function and then find the step response. Sometimes they will ask. In that case, the step response equal to what? 1 minus e power minus zeta omega n t sin omega dt plus 5. 1 minus zeta square. That is equal to what? 1 minus e power minus zeta equal to 0.69. Omega n is 2.896 t divided by square root of 1 minus zeta square 0.69 square sin omega d. Omega d is omega d equal to omega n square root of 1 minus zeta square. That is equal to 2.896 square root of 1 minus 0.69 square. You find and substitute here omega dt plus 5, where 5 equal to tan inverse of square root of 1 minus zeta square upon zeta. Like that you can write. Sometimes they will ask you to find the step response. Instead of asking zeta and omega n, find the step response. Unit step response. Already we have seen some problems on time domain analysis. Now let us see few more examples. Obtain the unit impulse response. Unit impulse response. What is the input? Unit impulse response means R of S equal to 1. And the unit step response means R of S equal to what? 1 upon S. This is the first input. This is second input. Obtain the unit impulse response and unit step response of a unity feedback system. Unity feedback system means H of S equal to 1. In fact, minus 1. H of S equal to 1. Whose open loop transfer functions, G of S is given. So we have to obtain the responses C of t for first case and second case. G of S is given. We have to find H of S equal to 1. Therefore, T of S equal to G of S upon negative feedback. That's why 1 plus G of S, H of S, but H of S equal to 1. That's why we can write like this. That is equal to 2S plus 1. 2S plus 1 upon S square 1 plus 2S plus 1 S square. So what you will get? 2S plus 1 upon S square plus 2S plus 1 upon S square. S square getting cancelled. Therefore, 2S plus 1 upon S square plus 2S plus 1. If it is unity feedback system, the transfer function can be, T of S can be directly written like this. Whatever the numerator for open loop system is same as closed loop system. There won't be any change in numerator. That's why we can write numerator as such, 2S plus 1. No need to derive all these steps. Denominator equal to sum of numerator plus denominator. Sum of numerator plus denominator. What is numerator? 2S plus 1 plus denominator, what is S square? That's all. You got the same. This is only if unity feedback system. Numerator you have to keep as such. Denominator, sum of numerator plus denominator. That's why we can write like this. Numerator is same as numerator. Open loop. N of S. Open loop. Numerator plus denominator. So if it is unity feedback system, if closed loop, open loop transfer function is given, means you can find the closed loop transfer function simply by keeping the numerator as such. And the denominator is nothing but numerator plus denominator. Now we have to find the response for two cases. One is 2S plus 1 upon S square plus 2S plus 1. This can be factorized S plus 1, 2S plus 1 upon S plus 1 whole square. Can I factorize like that? S plus 1 whole square, S square plus 2S plus 1. So the roots are repeated. Roots are repeated. Roots are repeated roots. -1, -1. Now, T of S is what? T of S is output upon input, R of S. That is equal to 2S plus 1 upon S plus 1 whole square. That is equal to R of S equal to 1. This implies for impulse, first case, R of S equal to what? R of S equal to 1. Impulse input, unit impulse input. Therefore, what we will get is C of S equal to 2S plus 1 upon S plus 1 whole square. We know the response for underdamped system. In that case, what is the nature of roots? Complex roots. Zeta less than 1 means complex roots. Here, real roots, repeated roots. Already we know that the roots are complex. Roots are complex conjugate. Complex conjugate means zeta is less than 1. So, underdamped response. For that, we know the derivation. That's why we can use the formula, we can write the response. Here we cannot, because the roots are repeated. Repeated means, what is the value of zeta? Repeated roots means zeta equal to 0. Sorry, zeta equal to 1. Zeta equal to 1. 0 means undamped. 0 means undamped. So, zeta equal to 1. Repeated roots means. In that case, what is the response? Smart response you will get. Smart response you will get. Third case, zeta greater than 1 means overdamped. In that case, roots will be again real and distinct. In that zeta equal to 1 means roots are real and equal. Zeta less than 1 means complex. Here, the fourth case is zeta equal to 0, undamped. It is oscillator. Undamped means oscillator. Always it oscillates with complex, with the constant amplitude. This is the case. So here it comes in the second category. Real and equal. We do not know the expression for C of t. We have to find. That's why let us factorize this. That is equal to A upon S plus 1 plus B upon S plus 1 whole square. S plus 1 whole square. A equal to d by ds of S plus 1 whole square 2S plus 1 upon S plus 1 whole square, S equal to -1. Therefore, these two getting cancelled. If we differentiate this, we will get 2. D equal to what? D equal to S plus 1 whole square 2S plus 1 upon S plus 1 whole square, S equal to -1. These two getting cancelled. If we substitute S equal to -1, -2 plus 1 equal to -1. Therefore, C of S, A equal to 2, B equal to -1. Therefore, we are getting 2 upon S plus 1 minus 1 upon S plus 1 whole square. S plus 1 whole square. Now we can find C of t, Laplace inverse. C of t equal to, this is 2 constant e power minus t. A equal to 1 minus this, instead of S, square is there. Therefore, we have to multiply by t. S plus 1 whole square. Therefore, t e power minus t. This is the response. So we have to derive no other go because we do not know the formula. Okay. This is for t greater than or equal to 0 because the response is from t is greater than or equal to 0. What is the initial value? Initial value is 2. Initial value, if you substitute t equal to 0, you will get 2. C of 0 equal to 2. What is the final value? Final value. Final value you will get infinity, minus infinity, multiplied with 0, undefined, but anyhow, minus infinity. As a limiting case, you will get as a limiting case, you will get 0. Let us check final value theorem. What is final value theorem? It is not asked, but let us check. C of infinity equal to limit s tends to 0, s 2s plus 1 upon s square plus 2s plus 1. That is equal to what? That is equal to what? 2s square plus s upon s square plus 2s plus 1. Limit s tends to 0. Limit s tends to 0. So 0, you will get 0 upon 1, you will get 0. But here, if you check, if you substitute infinity, you are thinking that it is infinity, minus infinity. It is not so because this is infinity, this is 0. 0 multiplied by infinity is undefined. That's why you have to find the limiting case. You can find this is undefined. That's why you have to find the limiting case. You have to find the limiting case. So while finding final value theorem will be very much useful. Okay. Now let us find step response. Step response. For step response, R of s equal to what? 1 upon s. R of s equal to 1 upon s. Therefore, C of s equal to 2s plus 1 upon s multiplied by s square plus 2s plus 1. In other words, 2s plus 1 upon s multiplied by s plus 1 whole square. That is equal to a upon s plus b upon s plus 1 plus c upon s plus 1 whole square. If you factorize partial fraction. Now we have to find a equal to s 2s plus 1 upon s multiplied by s plus 1 whole square, s equal to 0. That is equal to 1. B equal to what? B equal to s plus 1 whole square 2s plus 1 upon s multiplied by s plus 1 whole square. D by ds of that is equal to provided s equal to minus 1. Therefore, that is equal to 2 plus 1 by s. D by ds of that is equal to if you differentiate this, what you will get? Minus 1 s power minus 1 s square s equal to minus 1 s equal to minus 1, that is equal to minus 1. So b equal to minus 1. C equal to what? S plus 1 whole square 2s plus 1 upon s multiplied by s plus 1 whole square s equal to minus 1, that is equal to 2 plus 1 by s, s equal to minus 1 equal to 1. Therefore, C of s equal to 1 upon s, b equal to what? Minus 1 minus 1 upon s plus 1 plus 1 upon s plus 1 whole square. That is equal to 1. If you take Laplace inverse, you will get C of t. C of t equal to 1 minus, this is what? E power minus t, at, a equal to 1. E power minus at, a equal to 1. Plus t, because instead of s plus 1, it is s plus 1 whole square. That's why t multiplied by e power minus at. That's all. In this case, what is the initial value? C of 0 equal to 1. C of 0 equal to 0. C of 0 equal to, as t tends to 0, this becomes 1. 1 minus 1 equal to 0. This becomes again 0. This also becomes 0. That's why C of 0 equal to 0. What is C of infinity? Final value. This is 1. This is also 1. This is, if you substitute infinity, what you will get? Infinity, e power minus infinity equal to 0. Therefore, undefined. That's why you have to find the limiting case. Limiting case. Again, let us apply final value theorem. What you will get is C of infinity. C of infinity. It is not asked. Let us find C of infinity equal to limit s tends to 0, 2s plus 1 multiplied by s multiplied by s plus 1, s square plus 2s plus 1. S equal to 0, you will get 1. S equal to 0, numerator you will get 1. Denominator s equal to 0, you will get 1. Therefore, 1. The final value is 1. But in time domain, it is difficult to find the final value. Difficult to find. You should be well versed with mathematics. Then only it's possible, because it is undefined value. This is undefined. This is undefined. 0 multiplied by infinity is undefined. Why final value is required? Why final value is required? That we will see in the next class. Because steady state error is there. Steady state error means, suppose you are giving input, the reference is 1, but the system settles somewhere here. What is the reference? I want to ride the car at 60 kilometers per hour. But even if I give full accelerator, it goes only up to 58. It goes up to only 58. I gave full throttle, but it goes only up to 58. Then the steady state error is 2 kilometers per hour. Steady state error is 2 kilometers per hour. For that, we need the final value. What is the reference we know? R of s we know. In this case, R of s equal to what? R of s equal to 1. What is C of R of infinity equal to 1? Because step response means initial value and final value are equal. R of infinity equal to 1. C of infinity equal to what? 1. Just now we found. Therefore, error steady state equal to 0. Error steady state equal to 0. Reference also 1. Final value also 1. Therefore, error is 0. But in this case, it has some steady state error, because the reference is 1, but it reaches only 0.98. Therefore, the error is 0.02. 0.02. This error is called steady state error. Steady state means after long time. Steady state means after long time. We are giving input now. After long time, there is an error means that is called steady state error. So to find that, we need the final value. Already we have seen some problems on time domain analysis. Now let us see few more examples. A servo mechanism is used to control the angular position theta naught of a mass through a command signal theta I. A servo mechanism means a mechanical system used to control. Servo mechanism is used to control an angular position theta naught. Therefore, theta naught is the output of a mass through a command signal. Input is theta I through a command signal. Command signal means input. The moment of inertia of load is 200 kg meter square. The moment of inertia J means S square. And the motor torque at load is, motor torque is, that is the output of motor. The output of the motor is, the mechanical system output is 6.8, that is kT. K. The gain K is given. Gain K is given. The damping torque coefficient. What is damping torque coefficient? B. B. That is 5 into 10 power 3. Bs. So this is the mathematical model given. This is the mathematical model given. What and all given? The moment of inertia J equal to 200 kg meter square. And the motor torque K equal to torque at load equal to 6.88 into 10 power 4 Newton meter radian per meter per radian. And damping coefficient B equal to 5 10 power 3 Newton meter per radian per second. What is the mechanical system? Mechanical system will consist of J, K, and B. This is K. This K is gain, static gain, not spring constant K. Spring constant Ks. There are 3 constants will be there in mechanical system. Mechanical rotational system. J, K, and B. Or JBK. JBK. For spring. For motor, the spring constant is 0. You should remember that for a motor, the Ks is 0. Therefore, the mathematical model is K upon J. This K is static gain. K upon S square plus Bs. So here K, J, B are given. Ks is 0. Ks is 0. For spring constant is 0 for a motor. So these 3 are given. What is asked? Find the time response for a step input of 1 radian. Step input theta I is given. Theta I equal to 1 upon S. If theta I of S equal to theta I of S. Theta I of S equal to 1 upon S. Because it is step input. Step input means always 1 unit step input. The step input of 1 radian means 1 by S. That is given. For that, we have to find the response. Again, let us read the question. A servo mechanism is used to control angular position of a mass through a command signal theta I. The moment of inertia of load is 200 kg meter square. And the motor torque at load is 6.88 into 10 power 4 Newton per meter per radians of error. The damping torque coefficient is that is B equal to 5 into 10 power 3. Find the time response. It is not neither nor mentioned about open loop or closed loop. How to find the given transfer function is open loop transfer function or closed loop transfer function. This is the mathematical model of the system. Feedback is different. Feedback is different. It is not part of, sometimes it is part of system. Most of the time it is out of system. So system is given, therefore it is open loop. But where it is mentioned that it is closed loop system, it is mentioned. It is mentioned that a servo mechanism is used. A servo mechanism means a feedback system. Servo mechanism means what? Feedback system. So the open loop transfer function is given. G of S is given. G of S equal to K upon JS square plus BS. That is equal to 6.88 into 10 power 4 upon J equal to 200 S square plus 5 10 power 3. This is given. This is given. Open loop transfer function is given. But the system is closed loop. Servo mechanism means closed loop. Servo mechanism means closed loop. Servo mechanism means there will be a reference will be there. The system will be here. There is a feedback. That is the meaning. Servo mechanism means a feedback system. G of S is given. Now we have to find the C of S. Therefore, we have to find the closed loop transfer function. Open loop transfer function is given. It is unity feedback system. Unity feedback system. We have to find the closed loop transfer function. T of S equal to numerator will be as such 6.88 into 10 power 4 upon denominator is sum of numerator and denominator. Therefore, 200 S square plus 5 10 power 3 S plus 6.88 10 power 4. This is the transfer function. That is equal to, if we take 10 power 4 out, what you will get? This becomes what you will get? 6.88 upon 200 divided by 10 power minus 4. 200 into 10 power minus 4 plus 5 10 power minus 1 S plus 6.88. That is equal to 6.88 upon 200 multiplied by 10 power minus 4.02 S square. 0.5 S plus 6.88, or you can write 6.88 upon 0.02 S square plus 0.5 upon 0.02 plus 6.88 upon 0.02. Find the final transfer function in natural frequency form. Natural frequency form. For that, we know the formula. If it is underdamped, check whether it is underdamped or not. For that, we have to find the roots. Find the roots. Find the roots. (344.25) that is equal to 344 upon S square plus 25S plus 344. This is the final transfer function. Find the roots. Find the roots. Check whether zeta. Instead of finding roots, here what is asked? Find the time response. That's all. No need to find the roots. What is the value of zeta? We have to check. What is the value of zeta? For that, we have to compare this standard transfer function. What is standard transfer function? Omega n square upon S square plus 2 zeta omega n S plus omega n square. No need to find the roots. Compare this with 344 upon s square plus 25s plus 344. Here, omega n equal to square root of 344. 2 zeta omega n equal to 25. Therefore, zeta equal to 25 upon 2 square root of 344 equal to how much? Find 25 upon 2 divided by square root of 344. How much? Huh? Zeta? Omega how much? 18.54. Omega n also we required. Omega n equal to 18.54755. Zeta equal to 0.667.67. Zeta is less than 1. This is zeta is less than 1. Zeta is less than 1. We know for underdamped system. No need to find the roots. We know C of t equal to what? C of t equal to 1 minus e power minus zeta omega n t upon square root of 1 minus zeta square sine omega dt plus 5. Substitute the values 1 minus e power minus 0.67 omega n equal to what? 18.55 square root of 1 minus 0.67 square sine omega dt plus 5, where omega d equal to omega n, that is 18.55 square root of 1 minus 0.67 square, that is omega d. What is phi? Phi equal to tan inverse of square root of 1 minus zeta square, that is 0.67 square upon 0.67. That's all. If it is less than 1, we can apply the formula and we can write the final result. So what are the important points here? Servo mechanism means closed loop system. The given system is a motor, that's why K equal to, the spring constant is 0. Therefore, the open loop transfer function is K upon Js square plus Ps. K is 0. Ks is 0. Here, the numerator K is called static gain. Conditions plus 4 y of s equal to 8 x of s. Therefore, the output y of s upon x of s equal to 8 upon s square plus 4 s plus 4. 8. Here, omega n square equal to, find undamped natural frequency. That is omega n we have to find by comparing this with the standard differential, standard transfer function in natural frequency form. We will get 2 zeta omega n s plus omega n square. This implies omega n square equal to 8. Therefore, omega n equal to root 8. 2 zeta omega n equal to 4. 2 zeta omega n equal to 4. Therefore, zeta equal to 4 upon 2 omega n. Sorry, 2 omega n. That is 2 upon square root of 8. That is equal to 2 upon 2 root 2. 2 root 2. Therefore, zeta equal to 1 by root 2, less than 1. Underdamped system. Underdamped system. Now we have to find the damping ratio. Zeta also we found. Damped natural frequency, omega d. Omega d equal to omega n square root of 1 minus zeta square. That is equal to, what is omega n? Root 8 square root of 1 minus 1 by root 2 whole square. That is equal to root 8 square root of 1 by 2. That is equal to 2 root 2 upon root 2. Root 2 getting cancelled, therefore 2. Omega d equal to 2. Damped natural frequency also we got. Time for peak overshoot. TP we have to find. Time for peak overshoot. TP. TP equal to what? TP equal to pi upon omega d. That is equal to pi upon omega d equal to what? 2. Pi by 2. Or 3.14 divided by 2 seconds. 3.14 divided by 2 seconds. Peak time is not asked. Peak overshoot only asked. Okay. TP is not asked. Okay. Peak overshoot, MP is asked. MP equal to 100 percentage MP equal to 100 e power minus zeta omega zeta pi square root of 1 minus zeta square. That is equal to that is equal to 4.32 e power minus 1 by root 2 equal to e power minus 1 by root 2 pi upon square root of 1 by 2. 1 by root 2 square, that is 1 by 2. That is equal to 4.33% overshoot. That is we found. Then settling time, TS. TS equal to, let us assume that 2% tolerance. 4 upon zeta omega n. 4 upon 1 by root 2 omega n equal to root 8. That is equal to 2 root 2. 4 upon 1 by root 2, 2 root 2. That is 2 seconds. TS equal to 2 seconds. Hence, find the time response. It is an underdamped system. That's why y of t equal to 1 minus e power minus zeta omega n t upon square root of 1 minus zeta square sine omega dt plus phi. That is equal to 1 minus e power minus zeta 1 by root 2 omega n equal to root 8 t upon square root of 1 minus 1 by 2, because 1 by root 2 square sine omega d equal to what? Omega d equal to 2t plus phi, where phi equal to tan inverse of square root of 1 minus 1 by 2 upon 1 by root 2. That is equal to square root of 1 by root 2 upon square root of 1 by root 2. That is equal to 1. That is equal to pi by 4. So we can substitute pi equal to pi by 4, omega d equal to 2t. This is pi by 4. That's all. Today we are going to see some more examples on time domain analysis. The open loop transfer function of a unity feedback system is given by the open loop transfer function of a unity feedback system. Therefore, h of s equal to 1. H of s equal to 1. Negative feedback system. Therefore, closed loop transfer function T of S equal to, if open loop transfer function with the unity feedback system is given, the formula is numerator divided by sum of numerator and denominator. That is equal to numerator, that is K upon S multiplied by tau S plus 1 plus K plus K. Or we can write K upon tau S square plus S plus K. Or we can write K by tau upon S square plus 1 by tau S plus K by tau. K by tau. This is the given transfer function. This is the given transfer function. Closed loop transfer function is given, where K and tau are positive constants. K and tau are positive constants. By what factor? By what factor should the amplifier gain be reduced? Amplifier gain be reduced so that the peak overshoot of the unit step response of a closed loop system is reduced from 75% to 25%. Here, we can assume the system like this. Here I am putting K 1 by tau. I am taking that K outside. S square, not 1 by tau, tau S. S multiplied by tau S plus 1. Why I am writing like this, not this? This is closed loop transfer function. I am writing open loop transfer function. Open loop transfer function. The feedback is coming here. Negative feedback. H of S equal to 1. This is given. I am writing this K outside because K means gain. Gain means it is nothing but an amplifier. This is the amplifier whose gain is K. If amplifier gain equal to 2 means if you give 1 volt, it will make it 2 volt. The amplifier gain is 5 means if you give 1 volt, it will make 5 volt. So the K is an amplifier. Like that you have to assume. The open loop transfer function of a unity feedback system is given by, the open loop transfer function is given, where K and tau are positive constants. By what factor should the amplifier gain? Amplifier gain. It means the K is an amplifier. Reduced so that peak overshoot of the unit step response of the closed loop system is reduced from 75% to 25%. Earlier, the MP1 equal to 75%. Now, the MP1 peak overshoot is reduced to 25%. What is the relation between K and overshoot? K and overshoot. If you take the transfer function, you compare this with the standard form, omega n square upon S square plus 2 zeta omega n S plus omega n square. Here, in place of omega n square, K by tau is there. K is variable here. K is variable here. You can adjust the gain. So omega n is variable. Omega n is variable because K can be adjusted. The gain of this amplifier can be adjusted. The gain of this amplifier can be adjusted. That's why omega n becomes variable. As omega n becomes variable, omega n is variable. As omega n is variable, the zeta value will change because if you compare this 2 zeta omega n equal to 1 by tau. Therefore, zeta equal to 1 by 2 tau. Sorry, I'm confusing this with 1 by tau. Therefore, if you compare these two, what is zeta? Zeta equal to omega n equal to what? Because we have to substitute omega n. Omega n equal to omega n square equal to K by tau. Therefore, omega n equal to square root of K by tau. So, zeta equal to 1 upon 2 tau omega n, but omega n equal to what? 2 tau, omega n equal to square root of k by tau. That is equal to 1 by 2 root k tau. Am I correct or not? Zeta equal to 1 by 2 square root of k tau. So, if you vary this gain k, definitely there will be a change in zeta. If you increase k, zeta will decrease. If you increase k, zeta will decrease because the relation is 1 by 2 square root of kt. If you increase k, zeta will decrease. That's why what is asked, the closed loop system is reduced from the amplifier gain. By what factor should the amplifier gain be reduced? How much k has to be reduced so that overshoot is reduced? Will increase. This is one response. This is another response. Let us assume that here zeta equal to 0.7. For this, definitely zeta will be this 0.2. For this, zeta will be 0.7. For this, zeta is 0.2. This is 0.7. As zeta increases, overshoot decreases. Zeta increases, overshoot decreases. So, we have to reduce the overshoot from 75% to 25%. That's why we have to increase the zeta. Zeta has to be increased means k must be reduced. K must be reduced. If you reduce, zeta automatically will increase. Zeta has to be increased so that the overshoot should be reduced from 75 to 25%. How much? By what factor we have to increase k? Because if you increase k, what will happen? Zeta will decrease. Now we have to increase zeta. That's why we have to decrease k. We have to decrease k. The relation between zeta and k is 1 by 2 root k tau. That's all. Now we'll find zeta 1 equal to 1 upon 2 k1 t. Can I say like that? Because there is no change in t. There is no change in t, only k is varied. Zeta 2 equal to what? 1 by 2 square root of k2t. Two different k's. We have to find the relation between k1 and k2. For that, first we have to find what is zeta 1, what is zeta 2 we have to find. For that, the 78% and 25% are given. What is the formula? MP1 equal to 100 e power minus zeta 1 pi upon square root of 1 minus zeta 1 square equal to 75%. 75%. It means what? E power minus zeta 1 pi square root of 1 minus zeta 1 square equal to 0.75. Therefore, zeta 1 minus zeta 1 pi upon square root of 1 minus zeta 1 square equal to ln of 0.75. ln of 0.75. ln of 0.75. Therefore, we can find zeta. ln of 0.75 negative value. Therefore, what is 0.75? ln of 0.75. It's not given. Zeta 1 directly given. 0.091. This implies zeta 1 square pi square upon 1 minus zeta 1 square equal to ln of 0.75 minus sign. So this minus sign will getting cancelled. Therefore, zeta 1 equal to 0.091. 0.091. Similarly, we can find zeta 2. For zeta 2, what is the overshoot? For zeta 2, the overshoot is 25%. Therefore, we have to substitute 25% equal to 100 e power minus zeta 1 pi, zeta 2 pi upon square root of 1 minus zeta square equal to 25. Or we can say that minus zeta 2 pi upon square root of 1 minus zeta 2 square equal to ln of 0.25. This implies zeta 2 equal to 0.4037. Zeta 2 equal to 0.4037. 4037. That is second equation. First we got zeta 1 equal to 0.091. What is the relation between K1 and K2 we have to find? So substitute the value of zeta 1. Zeta 1 equal to 0.01, not 9, 0.091. Zeta 1 equal to zeta 2 equal to 0.4037. Zeta 1 upon zeta 2 equal to zeta 1 equal to what? 1 by 1 upon 2 square root of kt, k1t whole divided by 1 upon 2 square root of k2t. One upon k2. That is equal to 2 getting cancelled. Therefore, this implies zeta 1 upon zeta 2 equal to square root of k2t upon square root of k1t. Or we can say that zeta 1 by zeta 2 equal to square root of k2 upon square root of k1. Or we can say zeta 1 square upon zeta 2 square equal to k2 upon k1. That ratio we have to find. Zeta 1 square equal to what? 0.091 whole square divided by 0.4037 whole square equal to k2 by k1. Therefore, by what factor we have to reduce k? Therefore, k2 equal to by what factor? That factor we have to find times k1. K1 is higher. K1 is higher. That's why more oscillation. So from that we can understand two things. First, let us find what is that value. Zero point zero five. 0.0508. 0.0508 times k1. Suppose k1 is 1 means the present gain should be 0.0508. So we have to reduce by this factor. This is the answer. We have to reduce the gain by this factor. This is very, very important sum. We are understanding many things from this sum. Let us look at this. By what factor should the amplifier gain be reduced? We have to reduce the gain by 0.0508. Suppose the earlier gain is 1 means we have to reduce the gain of this amplifier to 0.0508. That is the meaning. Then the oscillation will be reduced. It means another information is there. If you increase the gain of the amplifier, if K of the static gain of the system increases, in closed loop oscillation will increase. If you increase K, what will increase? Oscillation will increase because zeta will decrease. That's why oscillation will increase. While studying about stability, we will study all those things. We'll see in the next chapter about stability. That time, this K will plays an important role. So if you increase K, the oscillation will increase. If you increase, zeta decreases from 1.7, 0.3, 0.2, 0.1, like that it decreases. If you further increase, what will happen? At one point, zeta becomes 0. Zeta becomes 0. Zeta becomes 0 means undamped oscillation. Always it oscillates, never settles. So that is also possible. By changing the amplifier gain, we can change the oscillations in the system. We can change the oscillations in the system. That's why speed is dangerous. If you give accelerator, you are increasing the gain K in the bike or the vehicle. If you increase, you are decreasing zeta. You are decreasing zeta. That's why suddenly something happens, you are oscillating. You cannot take the decision. That's why it leads to accident. Today, we are going to see some more examples on time domain analysis. Steady state error and error constants. Steady state error and error constants. Steady state error and error constants. Already I told you what is steady state error. This is output C of t. This is the response. Suppose the reference is here, R of t. R of t is here. Y-axis is C of t. In that we marked R of t. Reference. This is reference. But the system settled here. C of t, C of infinity is here. So there is a difference. Finally, there is a difference. It means I'm having a system. Let us take the car example. We are controlling by a closed loop. The reference speed is 60 kilometers per hour. Reference speed is 60 kilometers per hour. The final speed, even if you give full throttle, the speed reaches 58 kilometers per hour. If you didn't change the gear, it will go this much only. Even if you give full throttle, speed reaches 58 kilometers per hour. What is the response? The reference is 60 kilometers. But the system settled at 58. Reference is 60. This 2 kilometers per hour. This difference is called steady state error. This difference is called steady state error. So finally, the system settled, but some difference is there between reference and final value. That is called steady state error. We are going to study about the steady state error. Error constants. Some constants in this analysis is there. The constants are called error constants. That also we are going to see. What is steady state error? Steady state error, ESS, or we can say that limit t tends to infinity, because after long time, E of t equal to limit t tends to infinity, R of t minus C of t. R of t minus C of t. The difference between reference and output after long time is called steady state error. After long time, the difference between reference and output is called steady state error. If you apply final value theorem, suppose you know E of S. I know E of S. Let us assume that I know E of S. If I know E of S, how to find E of infinity? That is, we have to multiply this by S. Limit S tends to 0. S tends to 0. Limit S tends to 0. S E of S equal to E of infinity. That is by using final value theorem. Final value theorem says that E of infinity equal to limit s tends to 0, s f of s. Now we have to find E of s. What is E of s? E of s is here. E of s is here. E of s equal to what? R of s minus E of s equal to R of s, because R of s is the reference. What is feedback? Feedback is B of s, R of s minus B of s. E of s also equal to R of s minus B of s. If you take here, what is we are giving? C of s we are giving. It is multiplied by H of s. Therefore, B of s can be written as C of s H of s. B of s can be written as C of s. Here, what we will get is C of s H of s or H of s C of s. Just a multiplication. We can put either side. C of s H of s. Then what is C of s? C of s is equal to C of s is the error is amplified by the gain by the system. Error is amplified by the system. Therefore, C of s equal to G of s multiplied by E of s. Therefore, wherever I find C of s, I can write R of s minus H of s, G of s, E of s. E of s is function of E of s. Here, E of s equal to R of s minus H of s, G of s, E of s. Can I write like that? Therefore, I can write E of s. I bring all E of s one side plus H of s, G of s, E of s equal to R of s. Or I can say that if I take E of s outside, what I will get? 1 plus G of s H of s. G of s H of s equal to R of s. Or I can say E of s equal to R of s reference upon 1 plus G of s H of s. The expression for E of s is, the error signal is R of s upon 1 plus G of s H of s. If we take what is steady state error? Steady state error equal to what? Limit s tends to 0, s E of s. S E of s. S E of s. That is equal to limit s tends to 0, s E of s. S R of s upon 1 plus G of s H of s. That's all. Therefore, steady state error equal to limit s tends to 0, s R of s upon 1 plus G of s H of s. Steady state expression for steady state error is limit s tends to 0, s R of s upon 1 plus G of s H of s. In place of, what is the closed loop transfer function? G of s upon 1 plus G of s H of s. That is closed loop transfer function T of s. What is E of s? Replace G of s by R of s. R of s upon 1 plus G of s H of s. So this you have to remember. E of s. Unit step input and position errors. Here, the error constants we are going to find now. Error constants that we are going to find now. For that, input is what? Unit step input. It means R of s equal to 1 upon s. Unit step input. Position error we are going to find. Position error we are going to find. For that, R of s equal to 1 by s. R of t equal to what? Unit step input, U of t. If R of t equal to U of t means R of S equal to 1 upon S. We have to find steady state error. Steady state error equal to what? Steady state error equal to limit S tends to 0, S R of S upon 1 plus G of S H of S. That is equal to limit S tends to 0, S R of S equal to what? 1 upon S. R of S equal to 1 upon S, 1 plus G of S H of S. S getting cancelled. Or I can write like this, 1 by 1 plus limit S tends to 0, G of S, H of S. Can I write like that? So I can write like this. This can be called as Kp. This is equal to Kp. Limit S tends to 0, G of S, H of S equal to Kp means if you assume like that, then we can write 1 by 1 plus Kp, where Kp equal to limit S tends to 0, G of S, H of S. For unity feedback system, Kp equal to limit S tends to 0, G of S. For unity feedback system, that Kp is called position error constant. Kp is called position error constant. Position error constant. Kp equal to, if for a unity feedback system, Kp equal to limit S tends to 0, S tends to 0. For unity feedback system, Kp equal to limit S tends to 0, G of S. For non-unity feedback system, Kp equal to limit S tends to 0, G of S, H of S. Where Kp is called position error constant. Kp is called position error constant. So for unit step input, if you find steady state error, you will get Kp. That Kp is called position error constant. Now we are going to find velocity error constant. For that, the input is a ramp signal, unit ramp signal. The input is unit ramp signal. Unit ramp signal means what? R of t equal to t, that's all. T u of t. T u of t. What is the difference between t and t u of t? What is the difference between t and t u of t? It's only positive sided signal. Positive sided signal. It is, if you put like this, the meaning is t, when t is greater than or equal to 0. Instead of writing two equations, you are writing two equations. T, the R of t equal to t, R of t equal to t. When t is greater than or equal to 0, where t is greater than or equal to 0. Instead of writing like this, R of t can be simply t u of t, you can write. U of t exists only t greater than or equal to 0. Its value is 1. Therefore, R of t, t u of t, you can write. It means positive sided signal, t u of t. If we take Laplace transform, R of S equal to what? R of S equal to 1 upon S square. What is steady state error? Steady state error equal to limit S tends to 0, S R of S. That is 1 by S square upon 1 plus G of S H of S. That is equal to this getting cancelled. This can be written as limit S tends to 0, 1 upon S plus S G of S H of S. That is equal to limit S tends to 0, 1 upon S G H. That is equal to 1 upon limit S tends to 0, S G of S H of S. That is equal to 1 upon KV, where KV equal to limit S tends to 0, S G of S H of S. That is called velocity error constant, where Kv is called velocity error constant. Where Kv is called velocity error constant. What is position error constant? Limit s tends to 0, g of s, or limit s tends to 0, g of s, h of s, which is not equal to 1. We have seen in the previous slide. Position error Kp equal to limit s tends to 0, g of s, h of s. Here, what is velocity error constant? We have to multiply by s. That is the difference. You have to multiply by s. Velocity error constant means s, g of s, h of s. If you know velocity error constant, we can find the steady state error. If I know Kv, what is steady state error? Steady state error. If I know Kv, 1 by Kv, that's all. If I know Kv, I can find the steady state error. In some sums, they will give velocity error constant is this much. Position error constant is this much. Acceleration error constant is this much. Like that, they will give. They are talking about the system. If you give step input, the steady state error will be this much. If you give ramp input, the steady state error will be this much. If you give parabolic input, the steady state error is this much. That is the meaning. They are actually talking about the system. Velocity error constant means it is property of the system. Property of the system. So we can talk the property of the system in terms of position error constant, velocity error constant, acceleration error constant. Acceleration error constant is yet to see. Now, unit parabolic input will get the acceleration error constant. What is parabolic error? R of t equal to t square upon 2. Deliberately, we are adding the 2 in the denominator to make it ease in while finding Laplace transform. Therefore, R of s equal to have a convenient form in Laplace domain. So, 1 by s cube, you will get 1 by s cube. 2 getting cancelled. 2 getting cancelled. Therefore, 1 upon s cube we will get. To have a convenient form in Laplace domain, in time domain, we are taking R of t equal to t square upon 2. R of s is 1 by s cube. For that, what is the steady state error? Steady state error equal to that is E of infinity equal to limit s tends to 0, s multiplied by R of s. R of s is 1 by s cube upon 1 plus g of s, h of s. That is equal to limit s tends to 0. This you will get, this becomes 2. 1 upon s square plus s square g of s, h of s. Or this becomes 0. This becomes 0. Therefore, limit s tends to 0, 1 upon s square g of s, h of s. That is equal to 1 upon Ka. That is acceleration error constant, where Ka equal to limit s tends to 0, s square g of s, h of s. So acceleration error constant means you have to multiply the loop transfer function. G of s, h of s is called loop transfer function. G of s, h of s is called loop transfer function. Why? Take the diagram. R of s. Here you will have open loop transfer function G of s. Output is E of s. Here you will get h of s negative. If you find a loop, closed loop, G of s, h of s is there. That's why G of s, h of s may be called loop transfer function. So if you multiply by s and let s tends to 0 means you will get position error. Loop transfer function is multiplied by s square, limit s tends to 0, Kp equal to what? Position error constant, limit G of s, h of s, without multiplying by s. Kv equal to what? Limit s tends to 0, s g of s, h of s, s g of s, h of s. What is acceleration error constant? Ka equal to limit s tends to 0, s square g of s h of s. So these are the three error constants. Error constants actually define the nature of the system. Define the nature of the system. So I can say that I'm having a system which has a position error constant of this much, 5. I have a system which has a velocity error constant of this much. I can say I have a system which has a acceleration error constant of this much, I can say. So the Kp, Kv, Ka are talking about the characteristics of the system.